King's chair.
Pero esa no, pero ahí está
Good morning, everyone. So we continue our journey in atoms. So it's an immense pleasure to introduce Tony Pantev, a great humanitarian and a friend of mine of more than 40 years, who is going to continue our journey. Tony.
Okay, thank you. As always, it's a great pleasure to speak here. So, since we're talking about atoms, I wanted to, I'm going to say very little properly about atoms at the end to give you the somehow the application of the discussion. But I wanted to somehow go back to the origins of the story and show you one example which you could consider as a motivating example for the introduction of atoms. And then there will be one non-rationality application. So everything I'm going to say, so I'm going to talk about quadratic vibrations. And their interesting homological invariants, which will be the non-commutative Horst structures. And you've probably heard already that atoms are particular simplified versions of non-commutative Horst structures. And so this is a joint work with Rondonagi and with Ludmil, Maxime, and Tony Yu. So different bits of it. So there's like many moving parts. We make them together. So to introduce the story, I first want to start with a brief survey of non-commutative geometry in the context that I would like to introduce the invariants. Just say categorical non-commutative geometry. So So there are many flavors of non-commutative geometry, and this one was introduced, well, was envisioned by Bondel more than 40 years ago, and then Maxime actually introduced concepts rigorously and developed the theory from the bottom up. So in this world, a non-commutative space is thought of as a proxy for the shift theory on some variety. So you replace the variety by the category of quasi-coherent sheaves, or say perfect complexes on that variety, and you call that the non-commutative space. So you can say that the non-commutative space in this setting is DG category C, say linear over a field, if you're dealing with varieties over a field, and I'm gonna work over C today, and there is a slight like finiteness, finite generation hypothesis here, which says that it has all limits and colimits. And I'm not going to go into that, but just so that you keep something in mind. A typical example of this for commutative varieties, so commutative varieties, of course, commutative spaces are non-commutative in particular. So if X is, say, quasi-compact, quasi-separated scheme, then the category of perfect complexes on X is satisfies this property, so as a non-commutative is the incarnation of that scheme.
I guess with this definition you want quasi-coherent, right? Because you have complete and co.
Say it again.
I think if you want it to be complete and co-complete, you want to take in the like QC quasi-coherent.
Is the realization of X as non-commutative space, and okay, I'll put this in quotes.
I mean, perfect is not complete.
Okay, I'm putting this in quotes. To address what Pranav is saying, in fact, what you wanted to do is you want to take the completion of this guy. So you can either take the quasi-coherent complexes, and these are the compact generators in them, or you can take the category of incoherent complexes where the compact generators are the coherent ones. But so for in practical terms, whether you have the category of generators or the completion, it doesn't matter. So you can really think about it as the perfect complexes. And other examples that do appear in this story. So if say X is again quasi-compact, quasi-separated, and A over X is a sheaf, quasi-coherent sheaf of algebras over structure sheaf. Then the category of DG modules. In fact, I can take DG modules. Then the category, if I'm doing it like this, then the category of is a non-commuting space in this sense. And again, I'm going to put this in quote. Because, I mean, you really need to think about this in the homotopical sense. So if you really want to get the proper realization, you need to take first quasi-free resolution of this guy and take the modulus of that. Another interesting example is if you have a variety with a potential. So say this is a smooth variety. W is a function. Then is this good? Can I use this together?
Yeah.
Then the category of matrix factorizations, so periodic complexes of periodic perfect complexes on Y, in which the differential squares to the multiplication by W, this is the non-commuting space. And there are some other examples that you can concoct. I mean, you'll see another example in a moment. There are also physics interpretations of these guys. But what I want to focus on today, there is a notion, so this is like a general non-commuting space, and you can really do geometry with these guys. You have essentially all the tools of algebraic geometry for them, except that you don't have points in general. There is a class of non-commuting spaces which is particularly good and very easy to work with. And it's essentially the class that we work with all the time. And these are called geometric non-commuting spaces. And the geometric non-commuting spaces are the ones which can be realized as pieces of commuting spaces. So non-commuting space, let me give it the name C, is geometric if there exists a quasi-compact, quasi-separated scheme X and an embedding of, let me do it this way, an embedding of C inside the DG category of quasi-coherent sheets on X as an admissible subcategory. Meaning that the embedding has both left and right actually. So these guys are, because you can realize them somewhere in the geometry of a variety, they're really tangible. You can really touch them, and it's very interesting to study them and understand their invariance. And in particular, so one thing I didn't say, in general, NC spaces C have the rank of homology which is only Z2 graded, And it's not mysterious, it's the periodic cyclic homology of the category C. And this homology carries a non-commutative force structure. So there is an extra data that you can put on it, which is an analog of the Hodge filtration and integral structure, and they satisfy the compatibility conditions for a Hodge structure. So the analog of the Hodge filtration is a slightly tricky thing, and I'm not going to discuss it now, because we'll go to a particular set of examples where it will be actually an actual filtration. You can see. But so these guys carry non-commutative Hodge structures, and the geometric ones, the non-commutative Hodge structures of a geometric non-commutative space is concrete, can be described very explicitly once you are given the pair. And hopefully the example you'll see. So the geometric ones have
Number over the complex numbers.
everything's over the complex.
Complex numbers, yeah.
And you'll see what the story is about.
John,
Yeah.
is a matrix factorization thing always geometric, or?
The matrix factorization is it's a good question. I do not know. I believe it is. It's known that it's always geometric in the Calabi-Yau case. So you could put the, ask for this category to be Calabi-Yau, to have a Serfunctor. And one way to enforce this in the matrix factorization case is to require that you have a GM action on Y for which the potential is, so Y is Calabi-Yau, we have a GM action on Y, and the potential is equivariant, and the weight of the potential and the weight of the Calabi-Yau block volume form are proportional. In that case, this category is a Calabi-Yau. And in that case, we know it's geometric. But in general, it's not completely clear. In many cases, these matrix factorization categories, they come to us as homogeneous categories, pieces in homogeneous categories of singularities, and then they're geometric by construction. But I actually haven't thought about abstractly whether it is geometric or not.
In general, there will be Z-mod 2 gradient, right? So
Yes, everything is Z-mod 2 gradient.
But DQ core has a Z gradient. So isn't that is there an obstruction to lifting the Z-mod 2 gradient to a Z gradient?
Well, yes, in general, you have non-geometric spaces, but I actually don't know any explicit example. All the examples that we write by hand are really geometric. In fact, Orwell has this theory of geometric NC spaces where he says, let's start with geometric NC spaces and let's try to do natural operations on them. We can do excision, we can do fibers, co-fibers, we can do blow-ups. Think about any natural geometric set of operations that you can perform, algebraic and geometric, on NC space, on geometric NC spaces. Does this take you out of the class of geometric NC spaces? And he proves for all the collections of operations that it doesn't. it preserves geometricity. And in fact, some of the proofs are kind of ingenious. They're very tricky proofs. So it's not an obvious statement. Okay, but why am I talking about that? So there is a particular class of geometric NC spaces, which is interesting, and we should look at it. So an example will be to take X, say a smooth, and in my case it's always going to be smooth, so you don't need it to be smooth. Say smooth, say projective variety. You don't need it to be smooth, you don't need it to be proper, but in my case it will always be. And then take alpha, which is an unramified Browser class on X. So under the condition that this is smooth and projective, we have a cohomological interpretation of this. This is the second topology of the multiplicative shift of functions, and again, under the assumption that it's multi-projective, this has a very simple description. It's an extension of the torsion in the integral of third cohomology of X by the rational second cohomology of X divided by the rational algebraic classes and all the integral classes. So it's a torsion group, but a pretty big one, but it's explicit. And so any such guy gives you a jerk on X. So alpha corresponds to O star jerk. G alpha on X. So it's the Riemann stack whose modular space is X, and all the stabilizers are finite and cyclic for the order of alpha. And you can look at Dirac categorical quasi-coherent shifts on this Riemann stack, and it naturally decomposes into a coproduct of characters of the multiplicative group. These are the quasi-coherent complexes on which the stabilizer, so the stabilizer for these guys is the same at all points. It is the multiplicative group GM, and you want the stabilizer to always act with the character N. And these guys, each of them is a non-commutative space. So the one that corresponds to the tautological character this one is denoted by X, alpha, and it's called the category of twisted sheaves. Alpha twisted sheaves. The reason it's called the category of alpha twisted sheaves is because you can actually write those guys, and probably somebody already talked about this. You can write these guys by descent data, and the descent data is coherent complexes on open sets, gluing maps for the coherent complexes on overlaps, so that the gluing maps don't satisfy the cocycle condition, but satisfy the cocycle condition with correction alpha. And for the other guys, you get n times alpha. Right. So this is some mild twisting of the geometry of X, and it is a non-commutative space. It's a geometric non-commutative space. Because there is a Severi-Brouwer variety, which is a projective bundle corresponding to alpha of dimension the order of alpha minus 1. Well, the index of alpha minus 1. And this category is an admissible subcategory in the derived category of the Severi-Brouwer variety, but it also can be written as the category of DG modules of sheaf of Azumaya algebras corresponding to alpha. So these are central simple algebras which are locally isomorphic to the endomorphisms of that projective bundle, which is the Severi-Brouwer. Okay, so these are the spaces I want to focus on, so they're geometric and non-commutative in general. And the question is, so that's an example, but it's really the main example I will look at. There is a general question you can ask, which is when is a non-commutative space, say geometric non-commutative space, truly non-commutative? The non-commutative space is some category with some mild properties. How do you know that it's really non-commutative? How do you know that there is no scheme for which this category is the category of sheaves?
Is this equivalent to finding a Morita equivalence to a commutative generated?
Yeah. Mm-hmm. Yeah, so it's the same question. When is it equivalent to something? The shift theory on a commutative scheme. And so there are obstructions to that, but they're surprisingly hard to compute, and it's surprisingly hard to come up with examples of these guys which are truly non-commutative. So let me just.
Can I ask something?
Yeah.
So in your definition of truly non-commutative, you only allow schemes, or do you allow
schemes?
Okay, no derived stacks or
schemes. Yeah. And so this means non-isomorphic to the Kaehler of some well-axis scheme.
Like the quantum torus? Or?
No, the quantum torus is not a scheme. Scheme is just a usual commutative scheme.
No, I mean that's truly non-commutative.
Right, the quantum torus for an irrational slope will be a typical example.
Yeah.
Something truly non-commutative.
Truly non-commutative.
So let me show you a non-example. So if X over Q1 is elliptic K3. So it's a genus 1 vibration with a section, and you need a slight condition for everything I'm saying to be true. You need it to be valid. But suppose you have one of those guys, then the unramified Brouwer group is actually isomorphic to the Teichner-Farevich group. So if you take a Brouwer class, you can think about it in two different ways. You can think about it as twisting the elliptic vibration into a genus 1 vibration, if you view it as an element in the Teichner-Farevich group, or you can think about it as a J. And so every pair alpha beta Brouwer classes gives rise to a non-commutative space called D x beta alpha.
This beta is related to beta?
Sorry. And what you can show is since alpha and beta are both in some abelian group, so the pair alpha beta is in the square of that abelian group, the group SO2Z acts on that square. Acts on the square of any abelian group. And what you can show is that for every element in SO2Z, the x g beta g alpha is equivalent to the beta alpha. So they're the same non-commutative space. But you know, we have transvections in SO2Z, so in particular, if you start with beta being 1, you get that so, and this is just a direct example. So for example, these guys for Brouwer classes on elliptic K3s, they're always committed.
So what you just erased. So but with this n, what happens with this n?
N just multiplies alpha.
But even the one that you had.
Yeah.
So that isn't.
Yeah. It just once you have the generator, you know all of those other.
All of them.
Okay.
Is there always in the examples typically of this kind of question an arithmetic group?
No, not necessarily. You mean?
Like in the quantum terms, there is an arithmetic group.
You're asking whether the group of symmetries that would give you twists like that will be. No. Like for abelian varieties, for abelian schemes, it's not. There is some continuous part in it, but. Yeah, I mean there is some arithmetic portion, but but sorry. So let me so let me begin. So that's that's the end of my survey of non-commutative things. And so now I want to look at non-commutative guys like that come from vibrations by quadrants. Families of quadrants.
Is there something like the Tate-Shafarevich here?
Say
We
again?
will have something like the Tate-Shafarevich here? No.
Yeah, I don't want to talk about the general story, I want to talk about the example, but just very quickly, if we have a family Q over a base A, which is a family, I mean, you can do it with all dimensional ones, but I want to focus on the even dimensional ones. Even dimensional quadrics. So that each of them has two rulings. Then you get a double cover. A twiddle, as we call it, S over A, which parameterizes the rulings in the quadrics. And you get the universal ruling over the double cover, which is the Hilbert scheme of planes, half-dimensional planes in the quadrics. So you get R over S, the universal ruling. And so this is a projective bundle. Right? These planes are projective spaces inside the quadrics. So this provides a very So this gives you one of those juries. On it. So R corresponds to juror. So we get a non-commutative space, which is S alpha. And so now the question is, how can we detect if this thing is truly non-commutative? And there is a particular example of this will be if you take a four-dimensional cubic, smooth, containing a plane. Then the family of hyperplane sections through that plane gives you a two-dimensional family of two-dimensional quadrics, which is birational to the cube. So X blown up at the plane over some parameter space, which is also T2, is a family. This is the blow. X at the plane. It's a family of two-dimensional quadrics. And Sasha Kuznetsov invented a method for checking that these guys are truly non-commutative and check that this one is truly non-commutative. So, there's a theorem of Kuznetsov which says that if the pair XP is Noether-Lefschetz general, then you get a non-commutative, truly non-commutative Gerp on a K3. The surface S in this case, which is a double cover of the plane branch intersects.
Nice.
And he actually conjectured, so this is called the Kuznetsov component of the cubic with the plane. And he conjectured that, in fact, in general, he conjectured that for any cubic, the Kuznetsov component is an obstruction to rationality. He conjectured that if it's truly non-commutative, then the cubic is non-rational. And so this is what we are after. We're trying to understand when you take the non-commutative Horst structure on these guys, and view them as atoms which are obstructions to rationality, can we deduce from the non-commutativity that that it's really non-rational. And in general, knowing that something is non-commutative doesn't quite tell you that the atom doesn't appear in a commutative space. But the method which Sasha actually used to prove this identifies classes, Hodge classes, which cannot be Hodge classes in the atoms of any commutative variety, and that proves that indeed, in this case, this thing is non-commutative, and in fact, for any thing coming from a family of quadrics, if you can prove that it's truly non-commutative by the same method. So, yeah, so the story I wanted to talk about, which I'm terribly out of time, is about a different setup for which this happens. So the main example that I want to focus on is when we have an intersection of three quadrics in B7. And so we take X, which is the complete intersection of a net of six-dimensional quadrics. So A is some general P2 in the linear system quadrics in P7. So this is so I'm going to take a general guy like that. So this is a smooth fourfold. It actually gives you one of these judges, because these are six-dimensional quadrics. So it gives S a double cover of A. This is a smooth surface of general type. double cover branched along an octet. And you get two torsion Brouwer class. So a priori it's not quite clear that it's two torsion because these are 6-dimensional quadrics. So the Brouwer Severi variety that you naively get is P triple. So you know for sure it's 4 torsion. But in fact it's 2 torsion. So in fact, what happens is that this X always contains a line. And you can look at the incidence variety, which is the pair of O T and pi. T is in the parameter space of the quadrics, and pi is a plane inside inside the Grassmannian. So it's a plane inside Qt, such that it contains the line. And this guy is 4-dimensional. It projects to A, and as a family over A, it's a family of 2-dimensional quadrics. And it's also birational to X. So there is a incidence map, I'm not going to describe it, that sends you to X birationally. So this thing is called the hyperbolic reduction of the family of quadrics. So the family of 6-dimensional quadrics is secretly a family of 2-dimensional quadrics. It has the same discriminant curve and the same Brouwer class. And for this one, because it's a family of 2-dimensional quadrics, the Severi Brouwer variety is a P1 bundle, so it is 2 torsion. Okay, so it's 2 torsion. It's purely topological. You can check very easily that generically, for a general net, it's non-trivial. And now the question is it truly non-commutative? And yeah, so the theorem is that yes, it is truly non-commutative. So for Noether-Lefschetz general A or X.
What does Noether-Lefschetz general mean?
In this case, it means just that when you take this double cover, so X gives you always this double cover. Yeah. The double cover is, as I said, a surface of general type. Generically, you want it to have Picard number 1. So you can check that for a general point in the linear in the Grassmannian of A's, this thing has Picard number 1, and Noether-Lefschetz general just means that we are in that locus. So it's the complement of countably many subvarieties in the Grassmannian. So you have a Noether-Lefschetz general X. So again, this just means that the Picard of S is Z. This thing is truly non-commutative. And so I don't really, I was going to try to explain a little bit about the proof. When am I supposed to stop? In 5 minutes or in 10 minutes?
Well, we can get 10
in fact, the reason this holds, so this holds from a proposition which is part of this method of Kuznetsov, and that proposition says that if you take the topological K theory of X alpha together with the Euler K theory, and this cannot be the topological K theory of any scheme. And you only need to check for smooth projected guys because the category is smoothly projected. Smoothly projected. And the way this is proven is to show.
Maybe, so what does it say exactly? What is topological?
Yeah, so I'm going to say, yeah, so each of those categories, so I didn't talk about, I said they have cross structures, and particularly they have integral structures in homology. The way the integral structures are built is by building the topological K theory of the category. And in fact, it's not known, going back to Prana's question, it's not known for general non-commutative spaces, even smooth and compact ones, that the definition of the topological K theory works. So there is some lattice, so you can define topological K theory, but you don't know whether, when you map it by the Chern character map to the periodic cyclic homology, that it gives you a lattice. You don't know the analog of the Caehler cycle. For general ones. For geometric ones, it's actually trivial. And these are geometric, so. But in fact, let me just say, I can replace this. In this case, this is isomorphic to the numerical K theory. And the numerical K theory is just the quotient of the K group of the category by the kernel of Euler K. Or it's the same as the image of the Chern character map in the homology of X. This is something very specific. So for jerks, this is not true in general, but it's always true if you know that the class of the jerk is topologically trivial. And in this case, this class is topologically trivial. So this jerk topologically is trivial, but algebraically it's not. So in fact, you check that this thing cannot be the numerical K-theory of any variety. And the way you check it is to show, so this is done by showing that there are no classes let's call them A and B in the, say, numerical K-theory. This is S, sorry. There are no classes such that the lattice spanned by those classes with respect to the Euler pairing is isomorphic to the lattice spanned by 1 and the Chern character for structure shift for all. Also variety. If you have any variety, you can take the structure shift and the structure shift for point, compute the numerical K lattice with the Euler pairing. That's actually the same for all varieties of a given dimension. And this lattice is never isomorphic to this one. That's how you check that this thing cannot be the realized variety. So you need to actually compute.
Yeah. But it should be very easy. So what do you check exactly? What is the what's the invariant?
Yeah, I forgot now, but it's something like there is a single space of maps from this guy. I mean, the intersection of this and this is 1. The intersection of this, this with itself is 0. This with itself is 1.
And there you get that AB.
There are no AB for which this happens. That's what the calculation. That's the calculation that you need to do. And sorry, I'm 3 minutes. So let me just say how you do it for the cubic with the plane or for the intersection of 3 quadrics in P7. You do it by mapping this lattice by the twisted Chern character map in the non-commutative Koch structure. So the non-commutative Koch structure for this category. So the great thing about the great thing about this thing is it's geometric. We know it's geometric because it embeds in some Severi-Brouwer variety, but it also embeds in the Dirac category of X. And in fact, the Koch structure of this guy embeds in the Mukai Koch structure of the surface of general type S. And so there is a alpha twisted Chern character map that maps you from the K theory of this category into the Koch theory of S, twisted by alpha, which is the non-commutative Koch structure. And then you need to check for this, you need to compute the Euler pairing for that non-commutative Koch structure, which becomes the Mukai pairing, and check that this doesn't happen. So it's kind of tricky because you need to understand what the minimal twisted shift is on what the minimal twisted shift is on this surface of general type on Kuznetsov's K3, and it's a delicate analysis basically with the family of 2-dimensional quadrics. So at the end you can describe that minimal twisted shift as a Hecke transform of a conic bundle over a line inside A. And the numerics that prevent you from doing this are divisibility issues. So you know Kaehler transform at how many points with what centers, and you compute the image of this guy inside the image of this guy inside the homology of S, twisted by the exponent of B-field lifting alpha, and then you can compute the whole lattice and see that there are no elements. So it's purely computational, except that you need to find this geometric object that tells you what the positioning of this lattice inside inside the homology of S is. It's tricky because this twisted Chern character map is defined by using the splitting principle, and for the splitting principle you need the minimal objects. So you need to find it, and there is some fairly complicated birational geometry, both in the Kuznetsov's case and in this case, but it works out at the end. Sorry, yeah, and let me just say one more word at the end. So once you know that this is what prevents you from doing it, this is actually visible entirely on the level of non-commutive cross structures, and then you have to check that the breaking into the non-commutive cross structures into atoms doesn't mess this up, because you have projectors there that break the non-commutive cross structures into atoms, which gives you the birational invariant. And this is about the interaction of the atom decomposition with the integral structure on the homology, and that's so you can't really use the naive, the standard version of the atoms that we do, because we ignore the integral structure there, so you have to enhance them a little bit with integral structures and pairings. But for surfaces, it's not hard, so you can do it, and then you get that the intersection of three quadrics, which is not the lecture. So generally, it's not rational. By the way, this theorem that the intersection of three quadrics, not the lecture general intersection of three quadrics is non-rational, this is known. This is a theorem of Hassett, Pirutka, and Chinkel, but the method they use to prove it is completely different. They use degeneration and ramified Galois. Anyway, sorry, I'm going to stop.
Questions? Yeah, so if you replace the word projective there by the word proper, would that change anything?
No.
So that projective didn't use projective?
No, anything smooth and proper. Yeah, I mean, I could just inertia. It just, the local Courvois spectral sequence for a structure shift for point is not.
Other questions?
What's an atom?
Yeah, it's so I didn't tell you what the Koch filtration is on these non-commutive cross structures, and what it is, it's a connection. Right, so the periodic cyclic homology, it actually has a parameter in it, which is the dot element. It looks like a bundle over the affine line. And the non-commutive cross structure, it's a connection with the second order pole at the origin, the non-commutive cross filtration. And for varieties equipped with an ample class, you can construct the non-commutive cross filtration corresponding to the ample class viewed as a symplectic structure. And it's non-commutive, it's only Z2 graded in general. And the coefficient in front of the second order pole gives you an endomorphism of the periodic cyclic homology, and you can decompose the periodic cyclic homology into the generalized eigenspaces protected homomorphism. That preserves the connection. And so the atoms are those pieces. So an atom is just a non-commutative Koch structure. If you ignore the integral structure, it's just non-commutative Koch structure in which that endomorphism has a single eigenvalue. And modulo some equivalences, so modulo analytic continuation and blow-up equivalence and projective equivalence. That's what an atom is.
Other questions?
Yes.
Can you remind me the period of the Barre class in the case of the cubic torcal with the two-plane?
It's still two.
Still
Both
two.
the index and the
Does
period
it-
are two. Yeah.
Does it play a role in the fact that
No, it plays a role. So this pairing, so these lattices, this thing, they're three-dimensional, both in the general type surface in the K3 case. They're three abelian groups of rank 3. And this pairing is a rational pairing in which the denominators are at most 4, because the period and the index are both 2. And you're looking for an integral sublattice. So, I mean, of course, it depends what the matrix of the pairing is, but it plays a real role, that it's at most 4. So you get only halves or quarters. In fact, in the K3 case, you only get half integers in the matrix of the pairing. In the general type Chi, you get quarters.
All right, let's thank Tony again. So we will be office hours tomorrow at 4:30 after Mohammed's talk, but Mohammed and Max do not know about this yet. So I'll announce this once again.
No, it's not. It's after Felipe's.
Yeah, but Mohammed needs to talk before he gives. All right, so there's a coffee outside and we will reconvene in 20 minutes.
So we continue this discussion with the talk by Leonardo, who's going to tell us about the new ministers. Leonardo.
So thank you very much, guys, for like being here today. And so I'll more or less take from where I stopped, but I'll recall some stuff from my perspective. This thing that I'm concerned about, and this has been like always this, is about the geometry of these series. That you already know, like of course that's has nothing to do with algebraic geometry or mirror symmetry, anything like this a priori. But so let's like gradually growing my expectations about this, and then of course I will take some results that appears on the paper of the same title with Linogram and Ludmil, and then I'll just more or less in the middle of my talk to the end I'll be more really speculative and ask questions that I don't know the answer, but I expect that some of them are like not very much grounded, but I would like to better understand this. So I remember to you that this story, it begins like in the 50s, with the work of Linogram, where he was trying, and indeed he thought he had produced a counterexample to the Poincaré conjecture in dimension 7. So herein, I was told by sigma 7 some topological manifold that is homeomorphic. To the standard 7-dimensional sphere, but that's not this, but not the homomorphic. So that's why we call it Katzarkov. They pair differential structures. And there are a lot of open questions to this kind of geometry, admissible geometries for exotic spheres, even today. Because since they're like topologically so much look like a classical sphere, because they are homeomorphic, you would expect in some sense, if you at least take the first naive glance to this, that they should contain the same kind of like geometry. But it is still unknown. The existence of a Riemannian metric G on sigma 7 with positive sectional curvature. This is not known. In dimension 10, things get more dramatically. There are exotic spheres that do not even admit metrics of positive scalar curvature. And what we want to do here, and maybe combining with this theory of atoms and even with algebraic geometry in some other sense, is to try to understand if you can read this a posteriori geometric obstructions from variational geometry. That sounds like a bit strange, but I'll explain how we aim to approach this. But more important, the first step is try to connect the differential topology invariants with algebraic geometry ones. To then maybe try to find the obstruction on the metric to this. And as Lena explained, the first step that we did on this direction was to look to this concept of spherical duality. That is the spheric contest of this T-duality, as per Mugai. And the problem is that if you look then to all the possible pairwise homomorphic smooth structures on homo to P7 spheres, they form a group under the connected sums, and this group is isomorphic to Z28, and exactly 16 of diffeomorphism classes of Z structures. And I know what this series is. These are realized as S3 bundles over S4, and only 16. It misses 12. And to that, we show that in the N2 can fit as spherical to closed pairs. But something like dramatic happens then. Because as Lino pointed out in his constructions, these pairs that can be put in a spherical duality relation, they admit these descriptions as this kind of star bundles that I recall that. We're going to pick a principal bundle here with two different principal commuting S3 actions, and that can obtain as orbit spaces, stuff like this. But since these actions commute, this bullet action here, it descends to one S3 action on the sigma 7, and the star action descends to. So these actions here, they define foliations by the orbits. And it turns out that this singular foliations induced, so these spaces with these group actions, they turn out to have Morita equivalent foliations. And so their S3 invariant geometry is much constrained. So this indeed says that pairs fitting spherical T-duality relations have a very constrained geometry. So we cannot see exotic structures when you look to this perspective. That's like a serious issue that we now would like to circumvent. Because once we establish this, there is no more room to try to see whether these multi-structures can appear in some kind of relation. And this was like very good to give this new understanding of these spherical T-dual pairs, but then how to proceed, right? And one thing that I just want to bring to your attention as some kind of like side quest on this story before we proceed is the following. And I just recall to you that there is this theorem of Aluzade saying that if you pick an homotopy sphere in dimension 4k plus 1, and so if it is an exotic sphere, which does not bound, is not realized as the bounded, which does not bound. Parameterizable, advisable. Manifold. Then they're totally into bundles of these. Are not symplectic. Why I'm bringing this to you? Because you have here this hypothesis of these spheres not bound in parallelizable manifolds, and hence their cotangent bundle not being symplectic homomorphic. In dimension 10, the exotic spheres that do not even admit geometrics of positive scalar curvature, they do not bound parallelizable manifolds as well. It's like some tiny evidence of that maybe could be some kind of relation if we go to different questions in geometry. And it turns out that in dimension 7, all of them they bound parallelizable manifolds. All the exotic spheres in dimension 7 bound parallelizable manifolds. Keeping track of this fact and this kind of diagrams, then what you can do is the following. Once given a diagram such as this, let's say 1, once in hand 1, you can construct the analogous diagram, say Q, and now for the cotangent bundles. And they shall be equivalent to the symplectic model. Yes.
So in dimension 7, you have two exotic spheres. They are bounded by parallelizable.
They bound.
Eight manifolds. But are the cotangent spaces symplectic model?
Yeah, this is the thing. If we put them in this way and look to the actions, if you have a diagram such as this, and you always have this for 16 of the 7-dimensional smooth structures, all the smooth structures on 7-dimensional spheres, then you can take the fact that they fit in a diagram like this to show the thing you can build symplectic models. But this is like only possible because they fit this very geometric kind of diagram. So this proof is like very, very, very little topological in many senses once you know these geometric realizations. But still, it's missing 12 exotic spheres on that in dimension 7. So what does it mean? There is some numerology that I learned to enjoy with Ernesto, that if you look at this Hawkins talk on ICM long ago, he relates the Hopf vibration with the number 1/12 on the Fourier expansion of the Weierstrass function. By the means of these log transforms that I'll talk in a bit, we can map all the 16 on the same number 1/12. So, but they are missing 12 that cannot be mapped on this. And we don't know why is that, and maybe this is just a coincidence, or maybe this hides some deep meaning. We don't know. But this is the story from the point of view of S3 bundles over S4, and what you can say even a bit about their symplectic, the symplectic geometry of their cotangent bundles. Now we'll turn out a bit like more algebraic. And as a Riemannian geometry guy, if something like some geometry is obstructed for some kind of symmetry, meaning here we are looking to always to S3 invariant symmetries, so S3 as a group of symmetries. What you do is try to break the symmetry. So instead of look to this kind of S3 bundles, we are looking to S1 fibrations and later T2 fibrations coming from homotopy spheres as an attempt to try to break the symmetry and maybe like incorporate many other admissible geometries and try to perceive something as a result of this. So let me proceed back. Saying that, starting from the point where Lemi stopped, we will consider this hypersurface singularities here. K minus 1 plus VQ plus Z0 squared plus Z1 squared plus Z2 squared, where K ranges from 1 to 28. This is, so we have then like U, V, Z0, Z1, and Z2, the complex numbers, right? We have then singularity, isolated singularity in the origin. And if you take the image of 0 and localize on some sphere, then that I will denote here 6K minus 1, 3 as a result of B squared. Then B squared. These are all homotopy. K is different from K prime. And now for this kind of a hypersurface singularity family parameterized by K, we have all the 28. So we have the 12 that were missing also. And this is because like a hypersurface singularity, we can try to make some kind of algebraic geometry coming out of this. And this is what we shall do, and try to pose some questions and make some relations with these two different stories. This one, I started with S3 symmetries, and now, as you're going to see, with S1 symmetries. And show that they are indeed related because doing these log transforms that Lino mentioned yesterday, we can get all of the possible realizations of homotopy series and all of the possible quotient spaces for different vibrations that they may admit.
And here, which Ks are the 16 Ks?
That's a good question, and I don't know the answer. I could not compute it. Like, it's my favorite, I believe, but I don't know. I cannot say that's like from K1 to 12. I don't know this, but I can tell one thing that's very important, that's K equal to 1 is the standard sphere.
Yeah. But it's unlikely that it's 1 to 12.
Yeah, mostly like but I don't know, like, I tried in many ways to try to see this, and I don't know the answer. I would like very much to know, but it should be a way, but I was just incapable to do this. But it's good that you remarked this because let's say the following. For K equals to 1, this is diffeomorphic. This number S7. Okay, it turns out that these hypersurface singularities, same, they carry C star actions. And this is what we expected that it is, right? So you'll be lambda, you act on these points. In such a way that the Fk shall be a weighted polynomial. So we just put the complementary way. So you pick lambda, then you're gonna, since the power of U is 6K minus 1, you put this to be 6. Then now I put this to be 2, 6K minus 1. Then 3, 6K minus 1. Then 0. And lambda 6K minus 1. Z2. And when you look to this order space, giving out the node by VK, these are fun orbifolds. Fun orbifolds. And so there are many things that we would like to do with this fan article to try to see if we can perceive some kind of different smooth structure coming out of this. Since that these are fun articles, we can make sense of this chain of accumulators to them. And as I explained yesterday, we have this kind of blow-up formula to them. And also the notion of operational maps between orthofolds or stacks. One thing that we can show by these means, and that's like the very first thing that you may ask when you want to try to see some kind of operational geometry in these orthofolds, is that or K different from VIHREN, VK is now operationally equivalent as stacks. So you have the first algebraic manifestation of these different smooth structures.
And which invariant do you use here to prove it?
Jervis.
So you use a Brouwer
Brouwer
obstruction.
obstruction. But there is some question also that we could ask, that is, you can see this as like singular varieties, and you may ask, question, for which K, VK is a rational variety as variety. So rational as variety. And the expectation is to try to use this Tony's methods that he's explaining in his talk to try to answer this. Maybe we didn't do this, but we expect to do, and I'll tell what will be my dream if it happens. So I will say this as conjecture, but it's a dream. That is VK is rational. Then you may ask yourself, what is the reason for this? I don't know. I would expect this very much to try to better understand whether this could be true. But I don't know the answer for this. And once it is also established, maybe by using these methods that Tony was explaining that to these orthofunnels, could be the case that we can try to hook some kind of differential topology invariant out of this story. Okay. So any comments or questions so far? Anything related to this? So this is the story that we are trying to approach. We are trying to resurrect this old topic of differential topology of homotopy spheres, and try to match this with this new language that appears as atoms, but even derived categories. And we are going into this direction again, because here we just provided one vibration, that is, since this is 6 direction, if you restrict to the link of the singularity, then you shall have VK vibrations. We are considering this kind of vibrations. Yes?
Is the underlying topology of these VMs known?
They have some singularities, and but whether they are homomorphic or not, I mean, we did a computation, and that now I'm not too sure if it's completely right, but I have the impression that they are all homotopy P3s. All homotopy P3s. But I may be wrong here. I mean, we did a preliminary computation on this, and I'm not completely sure, to be honest. They are homotopy degrees, and you do this by using sequences and to match the topology of this. So I'll not write this precise. But then we have a S1 vibration. We could try to do like something different, because these homotopy spheres, they do not even carry complex structures, and also not like this. What we could try to do is cross with S1, and you may recall from Minosoft that that's what we call homotopy of So once we add this extra S1 there, we may ask also what kind of admissible.
You can realize them as elliptic vibrations, or you can realize them as elliptic vibrations.
I mean, in dimension 4, they are like examples of minimal elliptic vibrations, but I don't know if this contest makes sense in dimension 8, to be honest. I'm not sure about this. But of course, you have some vibration for k equal to 1 to p1. This you have, but I'm not sure. No, not p1, p3. To p3. You have a vibration to p3. Yes, with S1, S5. No, not S1, S3, S5 again.
But sorry, I was saying that these products with the circle are complex?
They are complex. Yeah, they are complex. These are, and that's why I call them homotopy
So
Hall.
they're like Calabi-Ekman, vibrations of Calabi-Ekman manifold.
Exactly, Calabi-Ekman. But it's like a very, very particular type of Calabi-Ekman, and I would like to make some comments on this before this part. Because here's the tricky part about the exotic spheres as well. These are homotopy spheres, and we took the cross with S1, right? Then there is this result of Rodolfo de Sapio in the 60s. That's the following. If you pick any homotopy sphere and you take cross with S2, this shall be always the diffeomorphic to S7 cross S2. Always. And if you take then S7 cross S3, sigma 7 cross S3, this will also will be the diffeomorphic with this. So indeed, the only way that you can keep track of these smooth structures is taking this cross product with circles. This is the only way. And now that we did this, we have this Calabi-Ekman, and they carry complex structures. We would like very much to try to understand what are the possible T2 vibrations coming out of this. So,
sorry, this is diffeomorphism, right?
Sorry?
This is only diffeomorphism.
Diffeomorphism, yes. Yeah. Diffeomorphism.
And can it be from bifuromorphism? So
Can it what?
I mean, this last one can it be bifuromorphism? Can it be holomorphic map? Or
Holomorphic map. I'm sure that there's like a full deformation theory when you put this complex structures, but we did not approach this. But I guess that they not need to be like holomorphically equivalent. You can try to put different complex structures such that they are not biholomorphic, but they are diffeomorphic. I think you can definitely do this, but we didn't do, to be honest.
thank you.
My pleasure.
But then, so our question is taking advantage of T2 to understand the variational geometry. Or even geometry as orbifolds of the possible outcomes, say, let's get this. Because the idea is try to use this extra S1 factor to produce a new different quotients and see whether you can indeed make it, maybe like choosing different T2 but keeping the case to produce two quotients that are not variationally equivalent but still come from different diffeomorphic structures. Because in this way you may be able to try to understand if like this is intrinsic phenomenon from differentiable structure.
And are they bona fide log transforms, or?
I'll talk about the log transforms now, but let's see. So the question is that we try to understand these possible quotients. We will never do operations on these quotients. We will always do these log transforms as I explained on upstairs. And what do I mean by this? So again, we have this question that is not a question, maybe like a goal. Try to understand the possible quotients coming from T2 fibrations for T2 actions on these homotopy Hopf manifolds, and we'd like to try to understand their algebraic geometry as orbifolds to see if we deform the action, then we keep the differentiable type of the total space. This still produces no operationally equivalent stacks or not, to try to see if like this is real phenomena from where we can try to extract some invariant or not. But to try to accommodate all of these fibrations, what we do is, as I recall, these log transforms for it holds in general for Calabi-Ekman with some care, but for homotopy. And the way that we approach this is very non-algebraic. It has its familiarities with eidetic fibration because it's a surgery in the end. But since these homotopy Hopf manifolds, they only are like complex structures, we'll only keep the track of these log transforms related to different holomorphic structures.
Did Lino show the Hodge diamonds of these W crosses ones? I don't remember.
No, we didn't, because we don't know exactly. For instance, we don't know for which case that diagrams can appear or not, for which sphere they can appear or not. Because you would have to do this Kronecker spectral sequence and then try to check, and to see whether this degenerates or not. We didn't do this.
Okay.
Okay.
But you could put it in our thing.
Most likely, yes. I mean, that's the expectation. But so I remember to you that all these exotic spheres, they appear in the work of Milner by the means of this plumbing construction. What is this? So you pick addition before, then you cross with S3, then you also pick here S3 cross this 4, let's write like this. You make the union, then you like have a common boundary that's S3 cross S3, and you promote some gluing. And here, conveniently, I'll denote by where these G and F are maps like. This. So you have D4 cross S3. And F is on S3 cross S3. And when I denote this del F and del G, I mean that's the restriction to this common boundary, so to make the glue. These are the diffeomorphisms. you have map as this, and all of the 16 homotopy spheres can be built by this kind of plumbing construction. But turns out that this plumbing construction gives rise to a bilinear pair by Newton that has P3, SO3, all times P3, and so forth. Is that a 7? And this shall be subjective.
You don't mean really 8, do you?
Is 8 because it's the boundary of a parallelizable 8-dimensional manifolds. 28, sorry, yeah, sorry. You have this bilinear map, and this is done just by this kind of. So if you know how to construct this from some special sphere by this plumbing, you indeed have a generator of this group, meaning that every other sphere can be obtained by taking connected sums with this generator. And so our log transform is definition is any map, any pair of maps same belonging to that's like diffeomorphisms. Of oops, sorry, I forgot something. Sorry. Sorry. We have this bilinear pair coming from the Milner construction, and then we want to put on the picture the homotopy hopper that didn't appear. So what we do, we cross here at S1, and then we cross here at S1, and we add just like the identity for the cooling here. It's just this. So now this is an homotopy hopper. There's like a Caehler type, and then we can define our log transform. And that our log transform shall be simply defined as let's denote like that. So this is sigma 7 process 1. The log transform on this phi psi is the manifold obtained by straightening the following angles. So you have this decomposition. So we have D4 S3 cross S1, D4 S3 cross S1, and then you do minus 1 identity, you compose with psi minus 1, sorry, phi minus 1 psi, and then we just change the clutching function on the plumbing. And for any of such a choice, you can regard it with a complex structure. And then you may ask, so how like these complex structures are like related, like in relation to this phi and psi that are maps? So we have this phi and psi.
And here you most definitely do not generate multiple fibers, do you?
No, never. Never. It's really like this is kind of fiber sum, and then what you do is just like changing the plumbing that you do, meaning changing the clutching function along this common boundary. That's it. But it turns out that it is compatible with complex structure, and analogous to this bilinear pair of Milner, you do have now a trilinear pair. So you have this diffeomorphism, and then there is a trilinear pair. There exists tilde, maybe I should always sigma. And these maps then come from P3 SO3 all times P3 SO3 all times P1 SO2 2. Oops. What's better here? Let's put this to this sigma 8 that I'll call this motor P of variables. Classes of the motor P of variables, model diffeomorphism. And this map, sigma tilde, generates sigma 8 completely. First generate sigma 8. So by the means of this log transform coming from these plumbing constructions, we can generate all multi-Hopf manifolds. All of them. But like as group, this is nothing but again Z28. So for theta 7, the group operation is connected sum. Now it's just this log transform. We can produce half of them using log transform. And then by the means of this, we can try to look to different kind of like ocean space coming from these vibrations. So we have in this map, we have a group structure here, and hence since we can generate, we can promote these realizations, we can now look to different kind of vibrations from sigma 7 plus this one to some space, let's say V. And approaching the end, the long-term goal is to understand V and its relations. Say something a bit about the derived categories quickly, but I don't want to pretend that I'm an expert on this. This is like Ludmil's style in many ways, but let's see what we can do. Coming back again to these vibrations, these decays, that again then can be generated outward by some kind of log transformation. Because of this map, this three-linear map. We saw that this here is independent by this Fk minus 1, 0. So that's one. So there is a hypersurface singularity attached to this. This Vk, they sit in a weighted projective space. That is nothing but 6 to 6k minus 1, 3, 6k minus 1, 3, 6k minus 1, 3, 6k minus 1. Alright, place it here.
So it's not well formed.
Sorry?
It's not well formed.
Because of
So all except layer 1 are divided by 3, so you can cancel this 3.
These last 3, right? Yeah, you can get rid of them because they are multiples, right? So they don't have a different group. The greatest common divisor is 1, right? Yeah. So this is something that can cancel. So this is they sitting.
But not quite as stacks, no? I don't know.
Yeah. So this is just one number, right?
So it doesn't work.
Yeah. Sure.
But you're seeing them as varieties, not as stacks.
Yeah. Now as well.
No, maybe something.
Maybe there's.
So you cancel 6 u minus 1 and also 3. So it will be like
Yeah.
2,
So
2, 1, 1, 1.
2, 2, 1, 1. Yeah. Right? We have this sitting here, and one of the ideas is try to see these guys, FK, that are hypersurface singularities. As after morsification, some you see this as like exactly like Lefschetz vibrations.
Sorry, what about the method comment? I didn't understand. I thought that you're taking this with the induced stack structure from the way.
On the first part, yes. Now I don't want to talk about the stacks because you can also treat them as
But the S1 vibration that you had was over the stack.
over the stack. Yeah, the before it was over the stack. Was considered over the stack. But I also asked the question about whether this is like a rational as a smooth variety. Sorry, a singular variety. VK. But
anyway, if you do have this stack issue, then that is a kind of a... Right, I'll
okay. So before I was considering this as a stack so far, Tony. Yes, that's true. That's true. Sitting on this non-formal weighted vertical space. Yeah. Then you have these hypersurface singularities. You can try to mercify the singularity, and I learned this from this Kutaki Ueda, result for base for advanced singularities. Okay, so we shall do this. Alright, so you can then try to look at this Kaya cycle of diversification, look to this derivative, and see whether, like, is there some kind of relation with dB of coefficients on VK, and some partial answer. There is a group action here, a finite group action on this VK. Finite group action. Such that when you look to this derivative, coherent shapes of, say, VK mod G. So this is G. Oh, sorry, G. Then this shall be, there are some exceptional objects here, and these are exceptional objects. And then as a final question is, how much ratings differential topology for me? Meaning how much you can still read from this derived category some kind of parts of the smooth structure coming from the link of the singularity? And the answer is that we don't know, but maybe, like if you try to recognize this, like using Harshit homology and try to see this atom's story related to this component, you can try to extract some kind of invariant out of this. And this is everything I wanted to talk today. Thank you very much.
Questions?
For the two maps that you constructed, from the W's to the space of manifolds of two boundary and half boundary, are these maps can be explicitly written in terms of the K, the parameter K, or just know them abstractly?
To that, I don't know how to get from this plumbing construction to this case, to this historic construction. I don't know how to do this.
Yeah.
I only know that since this generates the homotopy half, you can then understand what are the possible vibrations. But then how to explicitly relate the plumbing construction with this?
Well, I suppose if you knew, you could determine if which one of them are those of the 16.
Yes,
and so on.
yes. This is something that we did consider, but since we have to move on more or less, then we just abandon it.
Any other questions?
So here, what is the group G?
So this is because you have this weeks of fun singularity, right? So, all right, to you. Oops. It's okay. Let's. So you can see the ring of this. You can put a ring to this hypersurface singularity, and you can attach degrees to this, right? And so the degrees depends on the weights. And for this choice of weights, we can make a map from C star to K, where this is where lambda to some lambda over this 6 lambda 2 6k minus 1 lambda 3 6k minus 1 and lambda 3 6 0, and they'll take the copern of this one. So G the copern of R.
It's kind of group of here Kakashi swap, right?
Yeah. Exactly.
Yeah, exactly.
Exactly this, yes.
One more question. I don't even know if the question makes sense at all. But, I don't even know how to formulate it. But what about the four-dimensional smooth Poincare conjecture?
There are many issues there, right? Because so let me say something. Hyong shall present a very nice work also on some kind of log transform that is maybe different from this. I don't know, but maybe more general this and. Our approach in dimension 4 is a bit dumb because in the end what we want to understand is smooth structures, different smooth structures on this homotopy half. So in dimension 4 this is S3 cross S1. There's a result of a guy named Raphael Zentner that shows that any log transform that yields in the same homology results in a manifold that's diffeomorphic to S3 cross S1. So if you keep the homology, the homotopy of this S3 cross S1 after log transform, you end up in the same space. What we are doing in dimension 8 is showing that this does not happen in dimension 8 because there are different slope structures on S3 cross S1. Now S4, it doesn't have like a complex structure and anything like this. Then it's a bit like curious to understand what it could be asked in this contest. But there is also one.
What happens with S4 crosses 2? Do we know anything about that or not?
Yeah, so S4 crosses 2, it will always be diffeomorphic to S4 crosses 2 by the same results of the Sapien. And so the only way that you can stabilize, or sorry, not stabilize, you did the opposite, to keep track of the exotic smooth structures is crossing with S1. So if in dimension 4, it's problematic by many senses, like as you can see, and there is nothing but that we can say about it. I suppose, but I always treat from now on, like until now, let's say, 7 dimension is the first dimension where it appears in the exotic sphere. Let's see if it turns out to be true or not.
Very good, very nice. Thank you so much.
Thank you. There is a lunch announcement.
I don't have it, you know. I would assume that by induction, you know.
Third floor again?
Yeah, we should be at the same place, 3:30.
This one is good, I want to see that.
So which one are you?
Socialist, like.
Have I taken your seat?
Actually, my laptop doesn't have a USB. Right, but there's an email.
The other thing is, the thing is I don't know that but you can send it. I don't, but this I'll figure it out.
Because I'm the talk after this one.
Yes.
You can send it to some of the secretaries.
No, send it to me, and I'll...
It's old balance.
Okay, all right. Let's start our okay. Let's start our afternoon session. It's great pleasure to introduce on the
Other way around, but it's fine. Good.
Zen's. And today he talked about numerical decomposition.
Right. Thank you so much for the invitation. It's a great pleasure to be here for the first time. So, I didn't know how I could talk about something related to atoms, so I just wanted to make some general remark about the decomposition theorem, which might be very remotely related to the subject of the conference. This work is a piece, what I'm going to talk about, a small piece of my joint collaboration with Kamila Felizetti and Olga Trapeznikova. And it's related to a project I started 2 years ago to understand the intersection cohomology of moduli spaces. And since I was not an expert in intersection cohomology, so I kind of started from a somewhat of a naive point of view that I would like to describe, that finally I found helpful in obtaining our results. So maybe I will just begin with describing first, so I'll describe first the space, then a little bit more the invariance, and I'll explain what the decomposition theorem is in my way, and then how one can go about calculating its components naively. So the spaces, to which people who know me, I devoted my career to a large extent, is the topology we are going to study. There's this moduli space of the semi-stable bundles on a curve. So we take a curve, genus at these two, and we will look at the moduli spaces. So there's of degree 0, so I will not put the degree there, but degree 0 bundles on of rank R on this curve C. And so these are just bundles on C with some properties. So these will be semi-stable bundles. So to find semi-stability, you need to do something like this. You say that for all, so first of all, the rank of V will be equal to R, and the semi-stability is something like this, that if you take a proper subbundle, then it's what's called its slope decreases, so that the degree of W divided by the rank, well, actually just in this case, just the degree of W is less than or equal to 0. And so this is now a set of bundles, say, or a category of bundles, and now you divide this by an equivalence that's not isomorphism, but it's called S equivalence. It's based on the idea that if you have a vector bundle V satisfying this, this implies this. Right? So for any subbundle, the degree is negative this way. So in this case, these bundles we like, we call them semi-stable. And unfortunately, I will actually explain the classification up to isomorphism, which is usually not done. But as a space like this, this little wiggle here means a weaker thing than isomorphism. And so I will not exactly explain what this means, but roughly the idea, I will describe this set, however, up to bijection in the following way. So, so V, let me write down V is stable. Let me write down the definition of that. If the same thing is true, so sorry, degree of V is, yeah. So I will always assume that the degree of V is 0. So the degree of all the bundles are will be 0. If for all proper subbundles, the degree of W is actually negative. So it's a stronger statement than this one. So this is what we call stable bundles. And now MR is in bijection with the following set. It's what's called polystable bundles. So it's just V1 direct sum, etc. Vk. So these are just direct sums of stable bundles. So rank of V I is equal to some Ri, and the sum of Ri is equal to R. So it just means that the total rank of this direct sum bundle is this R here. And then Vi are stable. Stable degree 0. Okay. So I look at this is what's called polystable bundles, and now this is up to isomorphism. Okay, so I could also introduce it this way. The only thing is that when you construct the spaces using geometric invariant theory, then this point of view is more natural. But finally, if you just want to list the points motivically of this space, then it is just the direct sum of stable bundles satisfying this condition. So now the point is that this space is singular, with some exceptions. So MR is singular, projective, and of dimension, has some dimension, R squared times G minus 1 plus 1. Okay. It's a big space. So a lot of effort was devoted to calculating the topology of the variance of this space which are smooth. So for example, the degree, I set the degree to be 1 here, then this space is smooth of the same dimension, and then this was sort of a playing ground for calculating, for example, the famous anecdote to check the wave conjectures. The Harder and Narsiman actually calculated checked the wave conjectures using on this example by M1 and degree is 1, and then it turned out that by the time they finished checking the wave conjecture, they were proved, and then the calculation became a theorem. Okay. Anyway, so that was for the smooth case. Now this space is singular, and so for this, it's not cohomology, but the intersection cohomology will be calculated. And so this is what my talk is about that. But maybe actually I decided to be a little bit honest now, and I will actually tell you what the semi-stable bundles look like, even without this what's called S equivalence. So, so what that means is that if you take direct sums like this, to that there will be semi-stable bundles correspond. I'll explain it, and then it will be a bit more clear. So let's look at this. So classification of semi-stable bundles. Semi-stable bundles. So of course I'll just do it for rank 2. Well, if you want to understand what's going on here, I'll take points here, and then I'll explain what are the semi-stable bundles corresponding to. Okay. So obviously there will be sort of at least 2 types corresponding to the partition. So you have a partition of R into K pieces like this, right? So R is equal to 2. So there's partitions of 2. Well, there is 2 of them. There is just 2, and then there is 1, 1, right? These are the 2 possible partitions. So let's look at that. So so of course when it's 2, then it's very simple. That's sort of the smooth locus of the moduli space. So I'll write it this way, M2. So this is just the part where the partition is 2, and this is just the stable locus, stable bundles. And so I will, maybe I'll do a little table like this. So okay, so this is the partition 2, and so here V is stable, and there's only, so you take V, which is now stable, so there's K is equal to 1, and to that bundle it corresponds only 1 stable bundle V. So what you see here, you see the points in M2, and here you see all the semi-stable bundles that correspond to it, okay, according to this strange equivalence. You will see in a second. So then the next one is when it's 1, 1, but here I will need to separate into 2 cases. So when you have 1, 1, then of course this means that you have 2 line bundles. Any line bundle is stable, so 2 arbitrary line bundles. So it just looks like this. So that's the point in M2, according to this bijection. But actually, if you want to see all semi-stable bundles corresponding to it, then you will have a complicated structure. So you'll have the following thing. You will have either an extension this way, or an extension this way, or maybe you will have up to isomorphism, or you will have just the direct sum. Okay, so these are the 3 possibilities for a semi-stable bundle which corresponds to this point. Okay, and so actually these extensions up to isomorphism are classified by a group, so it's actually going to be PG minus 2. And then this one is also PG minus 2. And then this one is just a point. So this is just a single bundle. And topologically, what happens is that actually all these PG minus 2s are it's a non-Hausdorff space, are just collapsed to this point. So that's what happens.
May I ask a simple question a little bit back? So if R is equal to 1, isn't it just a Jacobian?
Yes, yes, then there is nothing.
So,
because
so
you see, this
case
there are no proper subbundles, so...
Yeah, so it's just...
yeah, and 1 is a Jacobian, yes.
Yeah,
yeah. So it starts being interesting, these two.
And for higher ranks, it became singular because of this splitting. I mean, Jacobian is smooth, but because...
Well, yeah, I mean, it becomes singular because the bundles have automorphisms, roughly. Yeah, for example. Okay, so I hope this is somewhat clear. So this is a non-Hausdorff sphere with this structure. Okay, so now the next one is a little bit more confusing. So you have now, when you have two bundles that are the same, then there's a different automorphism, so the situation changes a little bit. And so then you just have this, and then you have, I guess, the direct sum. So when I write this, I mean a non-trivial extension of the isomorphism. Okay? And so then what you will see is something like this. You'll have a PG minus 1, because now the extensions are bigger, plus a point, which again, a non-Hausdorff gluing of the whole PG minus 2 point. So that's what you will see actually. Okay. So this is what it looks like. So I describe honestly now up to isomorphism, but as I said, we divide by this equivalence, and the actual points are just that's what you actually see. Okay, so in particular for M2 it's very simple. I mean, roughly you just get if you subtract the stable locus, so this is the stable locus, then you just see roughly the Kummer variety. And so these are the special, if you divide by the determinant, the special 2 to the, whatever, G to the 2G points, special points in the Kummer variety, and this is the Kummer variety. Okay, so this is what the geometry looks like. So now, let me, I think I explained everything about the geometry that I wanted. Yeah, maybe just one thing is that let me here, I will write, so in general, I'll use in general this notation. So in any case, this is now a special thing that I'll use later, but just looking at this, roughly, obviously, M rho then, as a, well, what you could call it a decomposition, nothing to do with the decomposition theorem, so sorry, MR is a disjoint union of these M rows, okay? Where rho is a partition R1, RK, those ranks that you saw there, which is a partition of R, okay? So the important thing is this decomposition. Now we will want to understand the topology of MR, and so this, of course, this decomposition will be important. And it's basically a stratification, but not quite. So that's, as you can see here, you see there's a special points, but roughly it's a stratification. Now we will try to understand the topology of these singularities, and so the way we do that is that we introduce some sort of a resolution. Of course, resolutions are very difficult to construct for this thing, but we can have something weaker, and that's what we're going to use. And those are which are called parabolic bundles. And so par. Okay. And so this basically, in a certain very fortunate, clever rigidification of MR, which works as follows. So I will not describe in complete detail, because, but it's roughly is the following: is that you take now this data, so it's the same thing. B, C, all the same thing with rank equals R, degree 0. And now what you want is the following. You will fix a line L in the, so you fix a point P somewhere here in the curve, okay? And now you fix a line in the fiber, so it's just an R-dimensional vector space, and this is just a line. Okay, and then you say that you modify the stability a little bit, so it's basically, it's the same story, but when the degree of W is 0, so I won't repeat that phrase that you find here, then L is not in WP. Okay, so that's how you achieve. It's not important, but I just want to give you a flavor, roughly speaking, for this. And now this space is actually smooth, obviously dimension R minus 1 times more than this. So this has dimension R squared times G minus 1. And so so the decomposition theorem in general, the one I'm supposed to make a remark about, is about maps around, well, not necessarily, but in most basic case, map from smooth variety, say projective varieties, to singular ones, and the understanding of the decomposition now of the cohomology of this space in terms of what you see here, in terms of the fibers of this map. Okay, so that's what the decomposition tool is in very general terms. Okay. So now let's go to the actual subject, decomposition and intersection cohomology. So I guess maybe I'll just start with Delign's theorem. So I mean, let's look at this setup, but just in the smooth case. So let's just look at the map I, mapping from X to Y. We can assume that these are smooth projective algebraic varieties. Smooth, that's it, not necessary, but let's just, but it's smooth and important, smooth projective algebraic varieties. Let's assume that Y is simply connected for simplicity. So then the claim is the following. Well, everybody studies, of course, the Hopf vibration when you do topology. Now, the point is that if this is true, then the thing that happens for the Hopf vibration cannot happen here. So then the cohomology of X is just equal, so that's called this vibration. So it's a vibration of this fiber F, say. Then what is true is that as an HY module, this is just the tensor product of this. So check this for the Hopf vibration. Of course, it's not true, but it is true in this case for projective algebraic varieties. Okay. So the idea, the question of how to generalize this theorem now for the case which is singular, so for example, how to understand this situation. But the answer to the question is still the same. How to describe the cohomology of this X, which is smooth now. So how to decompose the cohomology of X, which is smooth, H star of X in terms of the fibers of pi. Okay, so this is what we're trying to understand, and that's what's called the decomposition theorem that I'll explain to you now. So for this, the point is that we need to have a good cohomology theory of Y, of the singular variety. So now Y is singular. So it's possibly singular now. And so this good cohomology theory is intersection cohomology. Okay, so the next thing is intersection cohomology, which is the good cohomology theory. Good cohomology theory for singular varieties. And so I'll just write down some basic properties. So IH Y is equal to just cohomology if Y is smooth. Now, an important point, and for me philosophically it's very important, is that it's not really a property, it's a non-property. So there is no product structure, but the whole philosophy that I'd like to describe is that I am interested in the product structure somehow nevertheless. So there is some avatar, some remnants of product structures that I would like to find here. Now you'll see in a second what I mean. Okay, so but there is no product structure, and there is a pairing. So there is so if dim y is equal to say n, then there is a map from m. So let's say to I m. M to say Q, so if you calculate over Q, so there's a Poincare pairing, and there's also what do you call Lefschetz isomorphism. So there is if let's say Y is projective, so you say omega is some ample class in H2. Then you can define the multiplication, and it actually gives you an isomorphism. So you have a map, say IH, I don't know, M, omega multiplied by omega to the T, to IH to M. Sorry, this doesn't M. So this is an isomorphism. So this is what remains from cohomology. So a lot remains except for the product structure, which is very important. Okay. Now, how to calculate in general is very difficult, and that's why this work is around. But I will explain you one piece of it, which gives you an iterative procedure, which in principle allows you to calculate it. And it's the following: is that you can so suppose an important example. But it's just an iterative example, is the following, that if you take a cone over a projective variety, so this is a non-compact version, but in any case it exists for that too. So so you take, say, sorry, let's call it M, M, you have an ample line bundle, and so then you take the cone, which means that you, in this ample line bundle, you just contract the zero section to point. Okay, so that's the cone corresponding to this. So this will be a non-compact variety, and the cone of L. So if you calculate the intersection cohomology of the cone of L, then this will be roughly the primitive cohomology. So this is not so important, but just to give you a taste of this thing. So the idea is you take a non-necessary singular projective variety, and now you take a cone over that. So you take some line bundle contracted to point to get a non-compact, even more single variety. Its intersection cohomology can be calculated from the intersection cohomology by taking the primitive part, which is the primitive in terms of this Lefschetz composition. Okay, so this is a minor, such an important thing, but just to give you an idea of what this looks like. Now, what is important, however, so this is not so important, is the following: that of course, when you calculate cohomology, then cohomology can be thought of with of some varieties, just the cohomology of the constant sheaf, which we'll write this way, Q, which is a rational number, is the constant sheaf on it. So for this case, there's also a sheaf, which is the so-called IC sheaf. So the intersection cohomology of Y is also, which of course reduces to this one, and Y is smooth, of the IC sheaf of Y. And so this can be slightly generalized. So the idea is that this is kind of a local version of cohomology. So in particular, if you look at the IC sheaf of Y and you restrict it to the smooth locus of Y, then of course it is just Q. So the restriction to the smooth locus is you recover the original bone. When it's not smooth, then it's a bigger sheaf. It's some bigger stuff. I'll explain what it is slightly. But now what I would like to say is the following. There is the what's called the intermediate extension construction, which somewhat generalizes this thing. So one way of thinking about what I wrote here, that if you take something on any say a flat connection, like a flat system, so here's just a trivial bundle, on the smooth locus of y, then you can extend it to canonically to a sheaf on the whole of y, which then gives us the intersection homology. So there is a construction that if you have now, so let's call the smooth locus here by y circle, okay, so that's the smooth locus. So if you have some local system on the smooth locus, then from here you can construct, you can extend it as similarly. You can take of IC of this L, which is now is going to be some sheaf again on y, and then you can define its cohomology, intersection cohomology as well. So this is just an analog, if you like, of calculating cohomology of a smooth variety, which is not simply connected on a smooth variety with values in a local system. So this thing here is a local system. Okay, so you start the local system, not a whole of y, but just on the smooth part. There's a canonical way, that's the construction I'm not explaining, to extend it to a sheaf on the whole thing, which is not a local system anymore. And then you just define the cohomology of this, which is just going to be the hypercohomology, if you like, of one of these values of this. So it just generalizes the usual intersection. So I will need this piece to explain what the answer here is. Okay. So now I have to erase some stuff.
So it seems that is a hypercohomology.
Well, or something, yeah. You have to take, of course, you have to resolve, but it's the same thing already true here, right? So it is obviously hyper. I mean, you have to resolve it, and then it's the same thing. You have to resolve it and calculate the usual thing. So I call it hypercohomology, so because now everything is cohomology, so it became a good. Okay? Yeah, that's basically the same. Okay, so now let's go, and now let's try to understand what's happening here. And so here's where I have a little insight that I don't get what this talk is about. So now, it's not a vibration anymore. What will happen is that y is singular, but x is still smooth. And by the way, this is also sort of Deline's theorem, but not quite, so I'll erase that for now, because it goes back to, but it's part of Deline's thinking as well. So smooth, this is singular, and then you can have an adapted, so that's not very similar to this one, y alpha, which is just a stratification, and of course it's constructed in such a way that for each point on some stratum, the fiber, so the inverse image of the point, is the same thing, which I'll just denote by f alpha, and this gives you a local system, so that's how this thing fits into that on each of the strata. And of course, this now, if it's this is a singular situation, these fibers will change if you change the depending on which y alpha stratum you're looking at, and generally the more singular the stratum is, the bigger this fiber will be. Okay? And I will explain what this is precisely in this situation. Okay, so you remember I just erased it, but there is a map now here from the parabolic smooth space to this MR. And MR has this decomposition, and I'll explain what the fibers of this decomposition is on for each of these strata, which are here parameterized by partitions of the number R. Okay, so now comes the part. The decomposition theorem, I find it very difficult to understand. The basic idea of this is the following, that there is a category, a special constructed subcategory, a special piece of the derived category of constructible sheaves on Y, which are called perverse sheaves, which turns out to be, in general, derived category is very complicated, but here the perverse sheaves are a special piece which is semi-simple. And roughly speaking, many people just say the decomposition theorem just says that the perverse sheaves are semi-simple. I find that not very instructive, so I'll give you something much more down to earth. But the key point is that it's semi-simple, and in addition, so then there's the simple parts, and the claim is that the simple parts are precisely this. So the first approximation of the decomposition theorem is a generalization of the Leibniz theorem, and it says the following, is that, maybe I will not especially even mention perverse sheaves, but the idea is the following, is that you have a sheaf that you call this way, they write it this way, so you take the on X, the constant sheaf, whose cohomology is of course just the cohomology of X, and you push it forward in the derived sense onto Y. So this is now a sheaf on Y, but this is actually it's a very natural sheaf. Roughly speaking, what this means is that if you take a little open set U inside Y, then the sheaf, the abelian group corresponding to this, is simply the cohomology of the inverse image. Okay, is what this sheaf is, roughly speaking. Okay, so that's what it is. Okay, and so what the decomposition theorem says, that this is sort of a perverse sheaf, so up to some sheaves, and so in fact the theory tells you that the perverse sheaves are all direct sums of this kind of sheaves. So it's just a direct sum for all alphas of IC sheaves of Y alpha and some L alphas. Okay, so this is a generalization. You have some local systems on each of the strata which then extended, and then their direct sum actually reproduces this potential. That's the statement.
You don't want the fiber in there somewhere?
Pardon?
You don't want the fiber in there somewhere?
No, I don't think. Why? Why do you need the fiber? You need the fiber?
It's fiber of the way.
Pardon?
It's in the local system.
Yeah, it's in the local system.
I think this is okay. Okay, and so a corollary of this, actually, it turns out then, is that that now if I take global cohomology, then of course this, when I push forward just to the point again, then of course I recover just the cohomology of X. So that's what we wanted, right? So then this will be just the direct sum of now this IH thing, IH of Y alpha, L alpha. I mean, you can maybe put the closure here is better. So, and this is what gives you the decomposition.
One of these pieces, Y alpha, can be smooth, I suppose, right?
And one of them is the main one, of course. So there's one of them, which is Y0, which I erased somewhere here, and we will come back to that. Actually, that's the point, in a sense. So to calculate, in fact, our purpose of our work is a recursive thing where, of course, one of these pieces, so one of the, for alpha equals, say, 0, Y alpha is equal to, so Y0 is equal to Y upper circle, so this is the smooth part. And so in our cases, this is simply connected, so this is just a finite thing. And so one of these pieces is precisely the intersection cohomology of the down space of M with some multiplicities, and since it's simply connected, it's just a finite tensor to the finite dimensional thing here. Okay, so this is now replaced, put in parentheses, is replaced by this thing. Okay, so I will not have time today to explain the recursion. So there's a recursive part of this whole thing which I will not talk about, but of course it's there. I wanted to say something else. And so this something else is the following. So, but what are these? So from general theory point of view, these L alphas are just some L alpha as well. But actually, so my first remark. So remark one. Then actually, to understand what L alphas are, if you're a topologist, you don't need to understand what perverse sheaves are, even though the theorem is very useful. And it's just the following. So this is the cohomological map. So the first one, the cohomological map. Cohomological map. And it's the following. So roughly you do this. So what is this L alpha? I want to construct it. And so it looks like this. You have this Y alpha, right? You take a point. This was P, just so I explained what it's explained here. This is this picture here, right? And so what I'm going to do, I will take a small neighborhood U. And it turns out, so yes. And so then I'll do the following. Of course, it has more difficult, complicated structure because there are other strata that come in here to this point. So I mean, it's not smooth enough. It's complicated. But in any case, the claim is the following: is that you can look at now the following space. So you can look at just pi inverse of U, and because of some basic theories, this is actually homotopy equivalent to just F alpha. So this is just homotopy equivalent to F alpha. Okay? And you can look at pi inverse of U. U minus Y alpha. So you throw Y alpha. And now we define what cohomology supported on Y alpha is. So what is cohomology supported on Y alpha? Well, obviously there is an inclusion map here, right? And so what I'm going to do is I'll take the corresponding cohomological map. This is a bit ambitious, I'm sorry. Now this is way too ambitious. So. In terms of space, so I have to redo this. Nothing is wrong with this, but I have to redo this. So it looks like this. I have H pi inverse U, U mapping to H pi inverse U minus Y alpha. Okay, this is the inclusion corresponding map. And now the claim is that L alpha is equal to the kernel of this map. So this is kind of a hidden secret from many people. I mean, the way they don't like this, but it is true. And in particular, L alpha is an ideal in what's a module in H F alpha. Sorry, so I didn't say this one is equal to H F alpha, right? Because these are homotopy equivalent. Okay, so this U is a contracts to the point, and its inverse image also contracts to the fiber, so it actually is equal to the inverse image homologically to the fiber. And then this becomes a subset. It's a kernel. It's simply a subset in this cohomology group, and the claim is that it's an ideal because it's a cohomological map. So it's a ring homomorphism. So its kernel is an ideal. Okay, so this is my first remark. And so in principle, to understand this decomposition and perform, for example, that recursion that we're talking about, I mean, you don't need to know anything else, but just calculate an actual cohomological map. Because this map to calculate could be very difficult. So, but nevertheless, conceptually, this is, I think, relatively straightforward. So that's what you need to do. And so this is what. And so let me now write down what this means. So of course, what the general set, and this will be important just to have an idea what this looks like, is the point is that, remember, so U is an open set, so pi inverse U is actually a smooth, it's in a smooth variety X. And so, so U open, so this means that pi inverse U is smooth in this X, right? Because X was smooth. And so because it's open, but of course smooth, non-compact. Okay. And on the other hand, F is so this is homotopy equivalent, but to F alpha, and F alpha is compact but singular. So that's our basic setup that we need to remember. Okay. So. Now, maybe I can formulate very roughly our first theorem. So this is from our work. Is the following. So this is an ideal, and the claim is that for each alpha, for all alpha, so now for all rho, so we have these rows here, right? We have that, so there's some modulus, something that I don't want to explain. So basically it's the issues that here, this L will be always 0, and I'm talking about this one. Okay, so that's the minor. The point is that L rho then is equal to H star F rho. So now in our case, this is story here, time a single element W rho. Okay, so it's generated just by one element. And so now the second, so I'm going down to the converging to the second remark that I wanted to make. And so remark 2 is to how to calculate this thing. Calculate the kernel of the cohomological geomet, this thing. I mean, so what is this calculation? Okay, so let me try to explain this now. And so for this, the idea is the following. So here I will give you a little more of the picture of what this looks like. So this F alpha is compact and singular. What it looks like, roughly speaking, is these kind of strange towers that, like a flower, that glue together. So the important thing is that F alpha is equal to a union, so sorry, F rho here. No, but this is here. So of course not in the general case, but in our case, F rho. So remember, rho is R1, it's a partition RK. So it has K components. It's a union of some towers, T sigma, each of which is smooth, and it's actually just a tower of projective spaces. So these flowers they're smooth, but they're glued together, and sigma is an element of the permutation group. So this K factorial elements.
Okay. So does that mean in particular you have this smooth and compact, that the whole structure of this cohomology is actually pure, because like it's...
It will be pure in our case, that's right. So it's a relatively simple case. On the other hand, if you want to calculate things that are in GIT situations, it's quite often will be the case. Of course, in the whole theory has other offshoots where this is not true, but here it is true.
But your argument seems to, that's why I'm confused. Your argument seems to suggest, like that discussion didn't have anything about your special case, like where you said U is open, so pi inverse of U is smooth, and this is homotopy equivalent to the F alpha.
That is all true. That's always true. This is always true.
Right. But doesn't that mean that whatever structure there is on there is going to be pure because the weights are going to be less than equal to something?
No. No.
Or maybe the dimensions don't work out.
No. Yeah, no, that's not true. Okay. But in our case, it is true. I document this. But anyway, it's even here. You need to prove that. So anyway, so the setup is this flower situation. Okay, and it's also true that the cohomology of the moreover, I'll write that here, that the cohomology of this F rho is actually embeds into the direct sum of the cohomology of these smooth spaces, T sigma. Okay, so these are now all smooth spaces. And so my second remark relates to what's called the refined intersection forms and excess intersection formulas. Okay, and so this is the following, that so the point is, this cohomological maps is still just a ring map, which is kind of so easy to calculate. I'm an enumerative geometer, so I want to transform it into some enumerative data, and this is of course well known, I didn't invent this, that this is related to something that's called the refined intersection form. Okay? And the refined intersection is the following thing, is that suppose you have exactly this situation, but in general. So this works even in general. You have some space Z, which is compact and singular, and you don't need anything for that. And this is in some X, which is smooth. Sorry, so now I denote it by X, but this is a slightly different X. Smooth, that means related. Smooth. And so then what the idea is that then there is a refined intersection form, which is an intersection form on the homology, say, of Z. And the logic of this homology is that you take a compact cycle in Z, you move it a little bit inside a smooth space, and there is no obstruction to that, so you can move it and then you intersect them, and then you get something. So here I'll call this, say, m-dimensional, so 2n-dimensional, something like this. So the point is, it's not like in the same dimensions as with Z, but it's as if the cycles lived in here. So this is smooth, usually non-compact, actually. Okay, and this is compact single. Exactly in this situation, this exists, and visually this is what it means. But actually, the way you can think about it, so we will assume what we know in our case is that the cohomology of Z is the same as the cohomology of X. In our case, this is true. And so in this case, and this is sort of this applies to the general situation. So then you can actually construct this thing in the obvious way, is that you have maybe, so let me, I was a little bit ambitious here again. So what I wanted to say is that you have Z in here, and then here you have, say, X minus Z, okay, something like that. And so what I wanted to say, so let's call this I and J. So then the idea is that I start with H, say, M of Z, so no, sorry, H, M of Z, and then this will go into the cohomology so now I don't want to explain exactly BM cohomology, etc., but this is true. And then it goes to minus M to H. Just check. Just 1 second. So it should be H2 minus X minus something like this. So this is an exact sequence. Okay. But what interests us actually is this thing. So this I lower star is the refined intersection form, basically, what it is, right? Because this exactly has the correct dimension. So just dualize. So if I dualize this one, then I'll precisely get the refined intersection form. Okay. But so another way of saying it is, so let me say this way of refined intersection form. You can also think of this thing, since it's defined in homology, as an element of H upper 0 tensor H, a symmetric element here. And so if you dualize this map, then actually this will be, a piece of this will be just H upper M. I dualize this space of Z tensor H. So you really just need to find an element in this space. Okay. And so the relation is that the current, this is our cohomological map. Basically, this is the same map, this one, as this one, and it really is just basically just the words are complicated. The annihilator of the inner product is really the kernel of this map. So we just need to find an element. Okay, so I'll write it down next to this in a second. And so so I have to repeat some things, but so I'm more or less at the end. So the point is that to calculate to calculate the kernel of the homological map, you just need to calculate this element. It is enough to calculate. Okay. And in our case, actually, so let me just write down sort of the final formula. But just to, I won't have time to explain, I guess, excess intersection formulas. But the idea is the following: we have this H F rho embedded into the direct sum of this H of these towers, which are smooth here. So it is enough to understand this refined intersection form on these smooth pieces, and these are actually just smooth manifolds. So T sigma and T tau. You just smooth manifolds intersecting in a bigger manifold, in a bigger smooth non-compact. So this looks very good. But now, just to understand the intersection form, you just they're intersected. They are not transversal in this big space. And but now this non-transversality you can resolve using excess intersection formulas, like something like this. It looks like this. That if you have two spaces, say the intersection of S in a big space T, it looks something like that. You take the actual intersection and then you. This I need to have somewhere. I didn't. Oh, this. Just a second. Yes, yeah. It's something like the normal bundle of S in X divided by the normal bundle of S intersection T in T, or something like this. Okay, so this is just an actual calculation, and since these varieties are smooth, all these normal bundles are well defined, and you just need to perform this calculation. Perform the calculation, and you get the answer, and I think I should probably stop here. Maybe I'll quickly write down what it is. This is a pretty result. So you remember I said that it's generated by one element, so L alpha was generated. I'll just write down the formula for that element. So this looks as follows. So these are these towers. So H2 of F rho is actually canonically isomorphic to H2 of all of these towers, T sigma, for all sigma in sigma k. And it just has the k variables. It can be identified. All the H2s can be identified to be just linearly x1, xk, some variables. And now that element W rho, so now L rho is equal to H of F rho times W rho, where a W rho is equal to, it's kind of a wild element of I less than j of xi minus xi minus xj. So this rho was these elements R over here. Ri, Rj times G minus 1. And yeah, something like that. So it's a completely explicit formula, and you just take the module generator divided inside, which you can calculate, and that will be your contribution to the decomposition theorem. So again, I just had two remarks. One is that it's really just a homological question of calculating the support, and if you look at it this way, you know that this thing is an ideal, which helps to identify what this thing is. And the other is that actually in fortunate situations when your fiber is actually, for example, it can be covered by smooth spaces, you can just calculate this kernel, this homological map using enumerative formulas and like this. Stop here.
More questions or comments?
So this result for arbitrary R, right?
Oh yeah, I mean, yeah, we did it, of course, for any R. Yeah, it's a bit confusing because I thought I would have more time and I would have explained to you what these fibers look like. So the fibers in this case, maybe I'll just do 10 seconds for this, it look as follows. So I described you these bundles, now you want to look what the fibers look like, and what happens here is that, so the fibers of the map now, so it's F2. So here, the fiber is just P1, which is just a choice of that line. So this is F. And here, what it is really just PG minus 1 times PG minus, but now not Hausdorff, and glued together at one point. And this is just going to be PG minus 1. And this point will disappear. So that's what it looks like. So this flower in this case is just 2 PG minus 1, so they are joined at a point. But generally, it's going to be more 2 factorial elements. So I didn't have time for that, so that's why I explained this one. I thought I would add this at the end. Yeah. Now, no, of course, yeah, it works in for any rank. Yes, yes.
And it's also kind of compatible for fixing determinants.
Oh, that's irrelevant. Yeah, of course. Yeah, that's a smooth map. Yeah, that's very smooth. It's a bit easier to write down the formulas with non-fixed determinants because the recursion is easier otherwise.
And is there some motivic interpretation of this calculation?
So, yeah, I mean, some way. I mean, what I can say, what there is, yeah, so there's several other things that come out of this. So one is that there is a, so first of all, there is a whole algebra interpretation of these formulas, which I didn't write down. These kind of, and I should have referred maybe some for Moscow and writing here, but which we used as motivation for our work. But in any case, so there is this whole algebra construction, and it's related to DT invariance, etc. And the other is that what I like this work, and this is unique to our work, which I hope is going to lead to some, is that you can understand the intersection pairings on MR, because it will be, MR will be, its intersection module will be embedded into this parabolic subspace. And so that's also some sort of motivic thing. And for me, what's most interesting is that the intersection product can be interpreted as a subspace of something that's smooth and projective.
Another question? If not,
actually, I have little remarks. Sorry, it's Maxim on Zoom. There is another very elementary way to understand intersection homology of singular variety. We take smooth part, It has boundary tubular neighborhood to infinity, and on tubular neighborhood to infinity, you take a half space which considers ice cohomology, take ice terms of weight filtration. It's like you fill by Fichte's manifold, and then this gives you a structure which is the notion of weight filtration. You can see it's more or less directly.
Mm-hmm. Yeah. So this uses the weight filtration. Yes.
Which is.
Yes. So that's also some kind of de Rham. You have a de Rham interpretation. It's relatively elementary. I was trying to say that it's relatively elementary. Yes. hanem azt mondja, hogy WP. WP a színvonalat részt.
Igen.
És a közül, és a azok körül kell venni a táblákat.
Thanks for the invitation to Ludmil and to Zillard who mentioned this to Ludmil and Ludmil called me. It's a pleasure to be here in this conference.
Actually, it was Mohammed.
Yes. Okay, well, Mohammed is not here, so I cannot take him. No. Okay, sorry. Sure. It's a pleasure to be in Sofia for the first time as well, and in this conference, I realize this place is not famous as Princeton, but it definitely brought a lot of famous people to this conference. And it's a great pleasure. Okay, so today I'm going to talk about this filtration cohomology, the ordinary quantum cohomology, which comes from the Hamiltonian floor theory, and that floor theory somehow takes Hamiltonians from some sister actions. That's the gist of the topic, and that's been some joint work with Alex Ritter, a couple of papers we wrote, and then by the end of the talk I'm going to mention the work with Zillard, where we use this filtration and compute it for some low-dimensional Higgs moduli spaces. So things interesting to algebraic geometry, and then we compare it to equal to W, and then with another filtration also coming from algebraic geometry. So that'll be the end of the talk, but before I want to explain how do we get this filtration, what's floor theory, and so on. So I realized that I'm actually one of the few people here who are more like symplectic than most people here are algebraic geometers. So probably I should kind of just make a very brief intro to what's floor theory, what are Hamiltonians, and so on. Because I heard this as an educational workshop, so I try to be not too harsh. Okay, so as I guess most of the people here know, so symplectic manifolds it's kind of an anti-symmetric version of Riemannian manifold, where you have two form, but it's not symmetric, it's actually anti-symmetric. But more importantly, it's a closed two form, which kind of tells you that there's no curvature in this geometry. So that's why we do more like a global invariance of this symplectic structure. So the simplest example is like R to 2n, and actually all symplectic manifolds are even dimensional because of this anti-symmetric property of the form. So in particular, if something is even dimensional, it's Caehler is a good example, and for people in algebraic geometry, smooth algebraic varieties over C are symplectic. So those are good, well, quasi-projective, let's say. So that they're Caehler and then Caehler is symplectic. So, okay, well, but if you're not necessarily looking at varieties, then you still want to have some complex structure. That's very important here for this talk. And just a general fact from some linear algebra is that if you have a symplectic structure, then there's always this almost complex structure, so not necessarily homomorphic. but I which squares to -1. And such that it's compatible with symplectic form, which means you take two of them and you join them, you get a Riemannian metric. So something similar like in the Caehler geometry, but you just don't have to be holomorphic. Like this I doesn't have to be integrable in general. Okay, this is just like recalling what are symplectic manifolds. Okay. Now let's talk about floor theory. So somehow symplectic topology really started with floor theory, and that was a big boost in the late 80s with Floor, and then with people who continued his work. And basically, so there's Hamiltonian floor theory, there's Lagrangian floor theory. Today we're going to talk about Hamiltonians, and of course Lagrangian floor theory can be seen as those things are, one can go from one to the other. So what we do in Hamiltonian floor theory, you study Hamiltonian flows. So those are very natural vector fields which come from you just pick a function on your symplectic manifold, and then you do something similar as in Riemannian geometry would be a gradient. So you pick a dual of your function, of the derivative of the function with respect to the symplectic form. So that gives you a vector field, and that vector field is then called the flow of the vector field is called Hamiltonian flow. That's pretty much all you need to know in order to understand what's Hamiltonian floor chain complex, right? So floor chain complex. So start with a function, you get a flow, you look at the flow, and you see periodic orbits of this. And then the generators of chain complex here, CFH, are the periodic orbits which have period 1. And now the differential is, of course, slightly involved. So it's somehow something like a Gromov-Witten, so it's like a Cauchy-Riemann equation, but you get perturbed by the Hamiltonian vector field. So perturbed pseudo-homomorphic cylinders. The pictures we have, so we have one periodic orbits, and then whenever you have a cylinder between them which satisfies this perturbed Cauchy-Riemann equation, then that's something you count. So in the differential, dy would be sum of the counts of these x. So in that sense, it's like Gromov-Witten theory, but just you perturbed with the Hamiltonian. So that's what the floor chain complex. So somehow the starting of talking about floor homology, and the upshot is, and that was the point of this was to prove Arnold's conjecture. And Arnold conjectured that the number of these periodic orbits here is at least as the sum of Betti numbers. And Floor's theorem, which says, okay, the homology of this complex give you the ordinary homology, then definitely the number of generators is bigger than the homology, and that's Betti numbers. So indeed, that was the case. And somehow that was the point of the story for closed symplectic manifolds. So if you want to think about closed symplectic manifolds, then this is what you get as an upshot. So the Floor cohomology, although it's very involved, it recovers the Morse homology and then the ordinary homology. But that's exactly not the point of today's talk. Like today, I want to talk about the open. I want to talk about the open symplectic manifolds, like Higgs moduli spaces, so things which have the C-star action, and that goes to infinity. And the outcome is that this Floor cohomology, this still works. Like the Floor cohomology recovers the ordinary cohomology, but that's only for the small Hamiltonian. So if your Hamiltonian there's some like C2 small, so there's some analytic condition you need to put, and that will still recover the ordinary homology. However, that's pretty much only when the story starts, but then you can go further and say, okay, well, I want to build some bigger Hamiltonians and see whether I'm going to get some bigger cohomology. Which brings us to symplectic homology, which is going to appear in the next line. But let me say, the big problem in symplectic topology and doing this floor theory is that there's always the issue with non-compactness and analysis of these things. So if your symplectic manifold is non-compact, if it has infinity, then these cylinders, you fix these x and y, the cylinders can go. There can be a sequence of them going to infinity. And that's a problem. So it's a non-compactness of the ambient, which can cause issue in counting these things. So you can make like infinite count. And that's why usually when a symplectic manifold is open, you assume it's Liouville. That's I mean, cotangent bundle, for example, is an easy Liouville, or any Stein manifold is also Liouville. That's Einstein. So Liouville means like if you're this is all like real geometry. So Liouville means that it looks like this. There's like a compact part which we don't care about, and then the open part is somehow some contact manifold times half line. So this is controlled, and also not only topologically, but like the symplectic form here is so symplectic form here is d of r alpha, where r is this coordinate and alpha is the contact. So all in all, the point of this Liouville condition is that so that you can deal with the non-compactness, so you can deal with analysis of these these PDs, these cylinders which you count in floor theory, and in that sense, so this is important. You also think about Hamiltonians which are linear with respect to the coordinate. So if you choose specific Hamiltonians which kind of follow this Liouville geometry, so this kind of control of the non-compactness, then you're still good. And then indeed, so the upshot is in one line that first of all these floor cohomologies, so things getting is counting these cylinders together with some natural continuation maps between them, they can define you the symplectic cohomology. So kind of, first outcome is technical, like this can be done, like because of the nice symplectic geometry of the Liouville manifold, but also other thing is that you can construct this kind of invariant of this open symplectic manifold, which doesn't depend on the joint, like you just get a single invariant. And as we saw in the very simplest open symplectic manifold, which is a cotangent bundle, this symplectic cohomology recovers the homology of a loop space, which is strictly, I mean, this is like infinite dimensional, so it's strictly bigger than the ordinary cohomology. So it's very interesting. It's interesting ring and it's very big. So this construction actually has some interesting impact. Okay, so that's kind of the outcome of what do we do about Hamiltonian floor theory for open symplectic manifolds. So the usual story is assume it's Liouville, then you get this symplectic homology, and then for like these easy, the easiest examples that this recovers something. The question is what it recovers for general open symplectic manifold. And the point is like we don't know. I mean, it's really hard. This stuff is really hard to compute. So even this was like a big theorem by Viterbo and then other people who kind of proved it in more details. So what we did, what Alex and I did, we assumed. See, under these assumptions things are fine. What we assume is that our manifold has this sister action, and then we use Hamiltonians coming. They're linear with respect to this the moment map of the sister action. So we use those sort of Hamiltonians, and we say symplectic homology is direct limit of those, and then let's see what's that.
So are these the homology of the category?
Yes, that's a good point. So for people who like think about mirror symmetry or so symplectic homology is going to be Hochschild homology of the wrapped Foucault category of this Liouville manifold. So this Liouville manifold with this nice structure gives you some nice Lagrangians to think about, which are either compact or they're Liouville at infinity. So they are invariant with respect to this Liouville coordinate, and that gives you this wrapped Foucault category for open symplectic manifolds, and its Hochschild homology is exactly the SH. Just the way Kontsevich said it in the compact case, Hochschild homology of the Foucault category is a quantum cohomology. So this symplectic homology in many ways it's kind of extension of a quantum cohomology to the open symplectic manifolds, and then there is indeed like a map between them. Okay, so to give you so this is on one hand what's going on, but what we really want to think about is the open manifolds which are not really Liouville, but they have this nice sister action, which kind of controls the non-compactness. And the first, the very easy example is C to the n. Now whatever I'm going to say for C to the n is very well known. So this is not new, but this is just to motivate it to say what we did for like general symplectic manifold with sister action, but on C to the n it's very visible. It's very easy to understand. Okay, so the first thing, so C to the n, we have a standard symplectic structure. That's what we've seen in the first slide. But then there's also standard sister action, right? Just the dilation of the vector, and then the moment map. So there's an S1 action which rotates, and the moment map, which is also, what is moment map? You have a S1 action gives you rotation. That rotation is a vector field, and that vector field is a Hamiltonian vector field with respect to this Hamiltonian. Okay. Now what's true for C to the n is that everything somehow gets together. On one hand, it's Liouville, so you have this Liouville structure. On the other hand, what's happening is that this Liouville coordinate, right? So this R is actually the same as the moment map, and your contact hypersurface, this sigma is the sphere. So the sphere, and then the radial coordinates is just the how far you're from the origin. Okay. So what happens there is, because it's Liouville, so as we said in the previous slide, we can construct the symplectic homology. So first of all, the floor homology is well defined, the continuation maps well defined, so this direct limit makes sense because of the Liouville structure. But just make sure that we capture this. These Hamiltonians are linear with respect to the radial coordinate, but the radial coordinate is the same as the moment map. So they're linear with respect to the moment. That's what we've taken in this example. That's kind of first observation. Okay, you can talk about symplectic homology here because it's Liouville. That's great. The second observation is actually that this ring, which, as we've seen for cotangent bundle, was very big. It was like the loop space. Here it's actually going to be 0, which is completely the opposite. And somehow I shouldn't say, but it does reflect that this is a contractible. But there are non-contractible, like you can get, there's like an exotic structure in C to the n which will give you a non-zero. So there's something further of what's happening here. And that's what we want to say, that this is because this comes from S1 action, and that S1 action gives you natural grading here. So let's pause for a moment. Okay, first, all these floor cohomologies, they're always Z2 graded, at least. Now to get the Z grading, you need to know something about your Chern class. So if your first Chern class is 0, if you're Calabi-Yau, in the symplectic sense, then you can grade your floor cohomologies. Because there's something about, grading is given by like going around your orbit. And then you see the symplectic flow on the orbit, and then you see how much it rotates your canonical bundle. Now your first Chern class is 0, if canonical bundle is trivial, so then that gives you like Z grading. That's one thing, and the other thing is first cohomology is 0, which means all the trivialization of canonical bundle are equivalent. So there's like a canonical Z grading. That's the outcome. In C to the n, that's again very easy. So then you use this grading very much in this argument because, so what did we say? So symplectic homology by definition is a direct limit of these. So what you have is you start. So this direct limit starts with floor cohomology of small Hamiltonian, which is just the ordinary cohomology of CTD. And then you go to the Hamiltonian with slope 1. And then you go to the Hamiltonian with slope 2, and then you go further. So then the direct limit you get this symplectic cohomology. But then what's happening here is very easy because think about, so there's a slope here, lambda, and what are the generators of this floor cohomology? Well, periodic orbits which are like one periodic with respect to the slope. But if the slope is irrational, then there's no periodic orbits. Periodic orbits here are just S1 action. So you can, if you take the slope to be irrational, the only periodic orbit is just going to be constant, just the origin. So what's happening here is these are all generated by the origin, but just the grading is going to be different. Because the grading then, as I said, is somehow defined by how much this canonical bundle is getting rotated as you go around. Now, because this is constant, pretty much just tells me how much the sister action rotates the canonical bundle. And that's going to be some number, but that number is always constant. So what you're doing here is that you're rotating more and more, because with the higher slope, we're higher in the slope. Slope is telling you like I'm speeding up the action. So I'm saying twice the action, or 3 times the action. That much I'm rotating my canonical bundle, and then what's going to happen is this is going to have something like maybe -2n grading, this is going to have like -4n grading and so on, which means that because continuation maps, they preserve the grading, the 0 actually doesn't get to 0 because 0 is here, so it immediately gets vanished. So the direct limit is 0. So the argument essentially uses the grading, which comes from here, but also that somehow the grading is really following how much C star action rotates the chemical map. That's the key point. And although like for C to the n, you can even write down this explicitly, the same kind of argument we go and use for whenever you have like a symplectic manifold with a C star action. So it's very general observation. But here for C to the n is very easy. We just have one fixed point. See, like this 0 was like a periodic orbit, but you can also think about 0 being the fixed point of the C star action. That's important for generalization.
So if you think of Cn as Pn minus divisor, is there any way you capture the mixed force structure of the homology of Pn minus the divisor with this symplectic homology?
So Cn to C is C like this. Cp minus 1 and Cpn.
Yep.
So what's the question?
So, I mean, to put it differently, there is mirror of the this category.
This is question.
So there is this. Sorry, the right category will comfort support on the sort of the mirror, which is Pn minus these things, and so the homology of Pn minus this has mixed force structure. Is it reflected on the symplectic homology anywhere?
Yeah, for that I wouldn't know, because what's happening with the mirror symmetry in this example, I'm not an expert. Yeah. Yes, but there might be a very good answer for that. That's true. Because for CTN things are very well understood. So I think there is a good answer. I'm usually not a mirror symmetry person, so I wouldn't know. But yeah, when we generalize this, then these spaces have God knows which mirrors because they're not labeled anymore. C to the n is, but it's very special. Okay, so then the third observation, so there's a couple of things we want to observe here and to kind of generalize for general symplectic manifolds. The third one is that you can actually get some spectral sequence here, and which starts with like just ordinary cohomology of C, or C to the n, and you get some further columns here, and these further columns, they're reflecting the S1 action, so the S1, just the orbits of the S1 action. Now you have like a S, so the picture is like, so you have C to the n, or in this case just C, and you have S1 orbit, that gives me this is cohomology of S1. But then what are the later ones are just the same orbits, but when you just apply more and more. So you have like twice the orbit, 3 times the orbit, and so on. How to see them all together, and how can I see all that? Because S1 action rotates everything. It's kind of at the same time. So the way to build this spectral sequence is exactly to make a different Hamiltonian. So to make a Hamiltonian which increases the slope, increase, eventually converges to some irrational slope. But by increasing the slope, you're kind of speeding up the action. So you're seeing, let's say here there's a slope 1, and then the next time there's slope 2, which means I'm going to see it's rotating in a faster speed. So that's I'm capturing this like twice the rotation, 3 times the rotation. So what we're doing here is, unlike in the previous, so in second observation, we considered very simple Hamiltonian. So this just lambda h, which had only one periodic orbit. That was the origin, right? So that one was good to prove that SH is 0. But this one gives you much more of a structure. So this Hamiltonian, which like here, increases the slope, and you get some periodic orbits on the way. because that also, there's natural filtration of this complex by the action functional, which here it just means you filter by where you intersect the y-axis. And as always happens in homological algebra, you can if you filter your chain complex, then there's a spectral sequence convergent to your homology. That's just general homological algebra. And the point is, if you let this lambda go to infinity, so you can just make this convex function, then this just goes to infinity, and this converges to your symplectic homology, because symplectic homology was the direct limit to this. Now, having that, so this is all just E1 page before the derivatives, before the arrows.
Which one corresponds to going, let's say, if you give a divisor at infinity, what corresponds to going around once, so it's not seen, cannot be seen here.
So again, was it so?
So I mean, let's say that I think of this open thing like
a CP1 minus
something, yeah, it is.
Yeah.
They should be apart, certainly the Caehler category, there is one which measures how many times you go around this divisor at infinity, what corresponds to this symplectic modular on many of these filtrations. You know, the question is whether the spectral sequence capture this going around.
Yeah, there's you mean you want to see it on the category side?
Yeah. Well, it's categorical also homology.
Yes, makes sense. Well, yeah, because on the homology there's just zero, but on the chain level, right, the chain level sees this, and right, yeah, see how much. So what is true is that the homology on the wrapped category of C to the n is symplectic homology. But then this is on the homology level. I don't know whether there's like a like only the chain sees these guys. So I don't know whether there's something that there's correspondence on the chain level. This is like this CO. Well, this should be right. This is a CO and OC map. Right, those are close to open string and closed string maps. I'll need to think about this. Maybe there's something. In any case, what happens is that this filters the complex, and you get a spectral sequence. And why this spectral sequence is good? Because, well, we'll see later. But for C to the n, what we definitely see is that you can get which are the arrows, because you know that it has to converge to symplectic homology. And we've seen in the previous slide the symplectic homology is 0. So if something has to converge to 0 in the spectral sequence, then everything needs to kind of vanish with each other. This is the ending, like the grading is not the usual P and Q. This is the P plus Q, which means that the derivatives need to go, differentials go like one up, one row up. So if this everything has to go one row up, then this has to be killed by this has to be killed by that, and so on. So you can a posteriori, knowing that symplectic homology is 0, you know what are the differentials in this floor chain complex. That's the outcome. Okay, so these are just like kind of 3 things to be taken from C to the n. Like you can construct symplectic homology, you see it's 0, and you get the spectral sequence. That's the outcome. And the question is how much you can generalize beyond the simple example of C to the n, which is like 20 years old, so it's nothing new. And can you get any applications from this, like in any direction you can think about? And the answer is so the answer is okay. What we started is thinking about these C-star manifolds. So C to the n you can see as a Liouville manifold, but you can see that everything was coming really from the C-star action and the S1 action. Because in C to the n everything somehow collapses. It's very, see, your basic example is always everything is true. But then you go further and then things diverge. So is it Liouville or is it C-star? So the outcome is, if you consider a symplectic manifold with a pseudo-holomorphic C-star action, I'm saying pseudo because it's not necessarily, you don't necessarily have a holomorphic structure, it's just almost complex, whose S1 part is Hamiltonian, so you can create a Hamiltonian floor theory, and you assume some further stuff, which we always see for like Higgs bundles or stuff. So the sister action has to be contracting, which means, let me just draw a picture, which means that's somehow control of non-compactness. So right, there's always a stupid sister action you can put, like T minus 1 on C squared, right? And that's a bad sister action. Like it has, some things get in, some things get out. In particular, your moment map is non-proper. So you don't, this is a bad for Hamiltonian floor theory. But if it's contracting, which would mean you have just positive weights, so things can get in the compact set, then things are fine. So in general, contracting would mean like you have some fixed locus, and then things get in that with the sister action. So there's like a compact point, which everything gets in. So this is like maybe like a differential geometric version of same projective. So in algebraic geometry, there was the same projectivity. This paper by Kaehler and Villegas, where they wrote some general results about those. What we did here is like we did this on the real geometric level. So just a differential, it's a real manifold with symplectic structure with this contracting action. So you get some all the results, but for this like more general, like real geometric structure. So the more important part of this story is there's a core, which is like for C to the n, that's just the origin. That's very trivial, but for Higgs moduli spaces, it's going to be like a central fiber of your future vibration. So the nilpotent core. Okay, this is just geometry part, like or topology part. All the important thing is that cohomology breaks, as in the compact case, to the cohomology of the fixed locus. So you have this fixed loci, and they carry all the cohomology information of your total space. And there is only a single minimal component because of the Bethe numbers here. Okay. Now to the point, to maybe the technical point of my work with Alex is, okay, can we do the same thing for C to the n? Like we started with C to the n, we see the sister action, and that gives us the symplectic cohomology at 0 and so on. Can you do the same game? Well, the problem is that the issue is that I never tell you what was the analysis behind, but there's some maximum principle which is satisfied for these floor cylinders. This floor cylinder is like a PDE, and then you look at PDE textbook, and it tells you, well, if you can make your symplectic structure so that this PDE satisfies some conditions, then it's good. And that's why Liouville is important. So C to the n being Liouville, which is you have the cylindrical end, was a technical point why symplectic homology works there. Now we got stuck in that. So what you have a manifold, you have a sister action, you have this contracting condition. So this contracting condition, it makes your topology or your geometry being thinged, but not necessarily your symplectic topology. That's the point. Which is you cannot talk about floor homology per se, but we got motivated by resolutions, by symplectic resolutions, which were the first examples we considered. So initially, this project started with me thinking about quiver varieties. So Nakajima quiver varieties or like categorical varieties, they all come as symplectic resolutions. So if something is a resolution of a fine variety, then that affine variety is in C to the n, and C to the n is Liouville. That's a good point. So, and that's exactly what we needed for this theory to work. So the point is, if you start with your symplectic manifold, and you take out some compact because it doesn't matter. If it projects to the end of Liouville manifold, then you're good. And so this sigma times, so that was this. So Liouville was like you have a compact part, and you have the cylinder. So the cylinder was the kind of the taming condition for Liouville manifold. So that's why we're saying, okay, well, if you have a proper projection to this like kind of tamed geometrically thing, then you're good. And you need to have some certain compatibility with like what's symplectic geometry here versus what's symplectic geometry here. Let's not go to details. But the outcome was, this condition says, okay, this is exactly what we need. But on the other hand, by looking at examples which we consider these symplectic resolutions, that's exactly the condition which you get for free. So so those we call symplectic C-star manifolds over a convex base, because this little manifold is often called convex or symplectically convex. But if you're algebraic geometry and you care about, okay, what examples are these? Like this is some like real geometric picture. Any sort of projective morphism to some affine variety with a sister action. That's always enough for this to work. And those are actually all examples which we always have in mind. Like why this implies this is because if you project to something affine and that affine has a contracting sister action, that means you can. So if something is affine, you can always embed it in C to the n. But if it has a sister action, you can embed it also equivariantly. And contracting condition exactly means that in C to the n, it's like positive weights, which is this something like this, t to the k, t to the k2. So that's kind of Liouville, and that's good. So the outcome is really the main example to think about is something which you can project to C to the n eventually, and C to the n is Liouville, and things are fine because we already see. So in particular, those will be quiver, hypertoric varieties, Higgs bonds, toric varieties, and so on. So you get a lot of interesting examples to work. Maybe I should say, because I didn't in this presentation I didn't talk more about toric varieties. What happens here is this symplectic homology, which we get for this construction, actually recovers. So for toric variety, SH construct this way recovers the Jacobian of the superpotential. So toric variety has this like a polytope or like a fan. From that you can get some this superpotential, this homological function, and this Jacobian ring is you just look at it's a polynomial, so you can do derivatives and so on. So it gives you some algebraic ring here, and that's actually isomorphic to the symplectic homology, which is very nice.
So what is the precise statement here? So why is something of this type?
Why is the same projected toric variety?
Same projective.
Yeah, and same projectivity. Just essentially, you say it's a GT quotient of C to the n. Because some people who talk about toric varieties consider just something which has like an open C star to the n dense orbit. But when I think about toric varieties, I always think they're GT quotients, right? So when, of course, and then it should be manifold, so smooth. When that's Y, then the symplectic homology which we construct on the next slide or the slide after recovers the Jacobian ring of the superpotential of this.
So that's his Oribach or something, some canonical. So that's some canonical W that just.
Yeah, which comes from looking at your polytope or the fan. I'm not a toric variety person, but if you look at the fan or the polytope, you can construct this W like just look at these vectors, you get a formula for your polynomial, and then the ring is created by doing like derivatives along the coordinates. So yeah, it's something which you can like write up very easily, and this theorem says that symplectic homology actually recovers this Jacobian, which is actually it's interesting. So it's interesting mostly.
So what does this symplectic homology cover this Jacobian? So this Jacobian, aren't they just finite, and the symplectic homology
but that's the thing. Yes, actually, yeah, that's a good point. This symplectic homology which we get here is going to be very non-typical, compared to the Kontsevich model where it was a low space. Yes, that's a good point. So, and that's exactly the point, because these are rarely Liouville. So see, manifolds with this like sister action and this, they cannot be even globally. Well, first of all, they cannot be Liouville because you always have this fixed C-star points. So by Stokes theorem, they'll give you like that your form is not exact. So that cannot be global Liouville. But even in infinity, it's hard because these are usually resolutions of singularities, and you resolve some singularities, it's going to give you like a lot of P1s, which again by Stokes theorem. So yeah, for Liouville manifolds, it's conjecture that it's either zero or infinite dimensional symplectic homology, like T star m or so. That's conjecture actually. But this is like a symplectic homology for a non-Liouville thing, which uses Hamiltonians coming from sister action. which then kind of makes it like the invariant you get somehow reflects the sister action, like this specific sister action. Or the torus, which we're going to see in the next slide.
So that isomorphism is your result, sorry, or
yeah. So what Alex, you can talk. Well, actually, you're not in Oxford anymore. But you and Alex had the office next to each other, so that was convenient. No, it was not a joke. It was just saying like it would be convenient if you were here. So this is
the person aside. That's the answer to the question.
Yeah. So this isomorphism Alex proved for toric varieties whenever they have some further analytic conditions, but which was this like convex level stuff. But now we realize actually any same projected toric variety, because it's a JT quotient, it has a map to the affine JT quotient, which means it falls here, so it works for. So pretty much the formula or the isomorphism was proved by Alex before, but now we're saying it actually works for any toric variety, not for those specialties. Yeah. So it's in his paper, I think 2015. I mean this previous result. Okay. Right. So this is like a general conditions which you need in order for the story to work, and then yeah, that's the observation. So you start with this manifold over a convex base, like this analytic condition. Then you can construct Symplectic homology using Hamiltonians which are linear with respect to this moment map. So again, comparing to C to the n, everything is simple. So this moment map is same as a Liouville coordinate. Here there's no more Liouville coordinate. The manifold is not Liouville at all. So we could be in a problem, but we are not, because we have this proper map which deals with analysis. And the Hamiltonians which you think about are strongly dependent on the S1 action or the sister action which you choose. However, what's interesting is, for example, for the toric varieties, see, for the toric varieties, this W doesn't know a particular sister action, right? So this doesn't depend on the sister action. And indeed, what's going to happen is whenever you have this morphism, this algebraic geometric example, where you not only have a sister action, but you have actual torus action, and you take any of these, a big torus like C star to the n, you have any direction you can take, they are going to be isomorphic. So the Symplectic homology, like here, it's not going to depend on a certain sister action, but on the kind of all torus acting.
All right, so I mean, since these examples were written there, are you going to claim that in all of these cases you get some rho P equal to W and your filtration sees any of this filtration, or these are different filtrations?
We'll see the comparison. Yeah. Okay. No, we'll see.
They're the same, or?
No, they're never. Well, they're same in one example.
Okay.
But that's just because of the chance. So what?
Which one is? We have 30 more minutes.
30 or because we started late.
Okay, go ahead. So I apologize. What example is this one?
This is low dimensional, like D4. You know the. Yeah, 106. Yeah, and that's when they all are the same. Yes, by chance. So. Okay, now so the question is, yeah, so the filtration is going to come in the next, because right, the title of the talk is filtration. We didn't get to the filtration, but that's happening now, because we cannot get it before this construction. Well, another thing which you remember in C to the n, there was some grading thing that gives us this SH is 0. That was it was written here. Like you have this direct limit, and the grading falls down, so everything goes to 0. That's what's going to happen here in general as well, as long as you have the Z grading. Z grading is necessary. And of course, seeing this example, it fails to be 0 if you're final. Like these toric varieties are often final, so they're going to use some non-zero SH. When they're Calabi-Yau, then it's going to be 0. Okay. Now, so of course, now how do you get to filtration? And on the other hand, what's the point? If SH is often 0, like whenever you're Calabi-Yau, then there's not much to talk about. You construct this like a very hard ring to construct, and you get 0. But the good thing is, in this direct limit, you get natural filtration coming for these maps, right? So this direct limit, I told you, you start with a small Hamiltonian. A small Hamiltonian is same as ordinary cohomology. At this point, we mentioned quantum cohomology for the first time. If you care about just the vector space, floor cohomology is same as ordinary. But if you care about the actual ring structure, then the floor cohomology of the small Hamiltonian is actually quantum. So there's this pair of pairs product in flow cohomology, T-cubic operation. You count pair of pairs, and that recovers the quantum cohomology when you Hamiltonian slope. So the outcome is, in this direct limit, you start with the quantum cohomology, and then you go further to floor cohomology to further slope. And because, what I tell you, so because the direct limit is 0, it means every class has to die at some point. And the filtration is exactly looking when the class died. So at what slope you get your class being going to 0. So it's canonically given using this construction. So you get a directed set, like a set of homologies, and you start with the ordinary homology, and you ask when my class dies in that. For what slope? How much I have to rotate my sister action so that my constant orbit gets killed by Hamiltonian orbit on the higher slope. That's what it is floor theoretically. So okay, that's the outcome and kind of the main object of today's talk. So you get floor theoretic filtration by ideals on the quantum cohomology, because this all maps, they're always like compatible, like quantum product, pair of pairs product. So the point is the kernel are always going to be quantum ideal here in the quantum cohomology. The upshot is if symplectic homology was 0, then this filtration completely exhausts the quantum cohomology, which means every class has to die. Otherwise, there's like you hit some biggest ideal here, and then you can just define the infinity filtration to be quantum cohomology. We'll actually see which ideal we hit in the last as the last non. Which one is the last filtration ideal, which is not the whole QH. We'll see that in the next slide. Okay, so this filtration, because of these maps, are all compatible with the grading. It's also on each grading piece you get filtration as well, which is going to be important if you want to compare this to perverse filtration. And yeah, very interesting thing is, although we've seen that this symplectic homology, like here, doesn't depend on sister action, this filtration actually does. And we'll see in the examples that actually, you pick different sister action, you get different filtration. So, which, like in Higgs modular, it's easy because you have just one sister action, so it's kind of canonical from the sister action. For the toric varieties, then actually it gives you different invariants. And another very important thing to say, well, this is filtration on quantum cohomology by quantum ideals, but for people who are more like, I want to think about the ordinary cohomology, what you can always do is, this is like your Novikov. So all floor homologies and quantum homology, it's always it's a homology over Novikov ring, right? So like a power series or Laurent series. So if you put your power series parameter to go to 0, so kind of to forget about all this quantum stuff, then you get, from this you get the filtration of the ordinary cohomology by the cup ideals, because the quantum product is cup plus this higher T operations. And higher T coefficients. So the upshot is then you can think about this filtration. And actually that's the one which we compare. Because perverse filtration and filtration on the ordinary cohomology as well. So that's the relevant one for, let's say, applications or comparisons. Okay. So let me just say as a general thing, because this is coming from floor theory, and in floor theory things are hard to define and even harder to compute. Even when you define something like, for example, symplectic homology for Livell manifolds, we know what is it for cotangent bundle, but if I give you a Stein manifold, what is symplectic homology, it's really hard to say. Unless you know that you can cap it with a divisor, like a normal crossing divisor, but it was also very hard work to get that formula. So needless to say, this is...
So when it's a complement to a divisor, do you compute this directly or by Miller symmetry?
Well, there's a big work of that's Ganatra, Pomerleano, Leiter. Yeah. Like it's a you do this spectral sequence and then yes, and but that goes well with mirror symmetry. I think that connects well to the Gross Siebert stuff. I'm just going to say like this filtration is because it's defined using floor theory. You never go and compute these cylinders. It's like in practice it's really hard. But at least what we know is usually some partial information. And for example, what we definitely know is that what's this filtration for the integer slopes. So the thing I didn't mention is, these slopes of these Hamiltonians and where this filtration is going to change is always when you get a period of your S1 action. Because everything started from this C star action, right? So the Hamiltonian orbits are S1 orbits. So in this directed system, things change whenever you have a new S1 period. So in particular, you can think about the filtration level when you get an integer amount of S1 rotating. And that's connected to the Seidel element, or in algebraic geometry, they call it shift operator in like Kunkov's work. So that's something which you get canonically from this S1 action using some symplectic. It's like a Gromov-Witten invariant. What I'm saying here is that Alex proved that they are very connected, all this. So symplectic homology using this S1 action is connected to the quantum homology, and it's a localization of quantum homology using this Seidel element. It's actually the way how you can see this, because the new quantum homology of the toric variety, as Alex proved, is going to be ordinary homology of toric variety is like these toric divisors, and then you have these Stanley-Reisler relations. What's going to happen for quantum homology? You get the quantum version of those, and then you localize. Okay. So all I want to say is like you get some partial information on this filtration, and this Seidel element, we can see it as a Lefschetz dual of this minimal component under certain conditions. So for a very small, for very like basic example of A1 resolution. So A1 resolution is like cotangent band of CP1, which you can see as resolving A1 singularity. Right? That's like the simplest symplectic resolution, if you like. There, the natural C-star action, of course, is dilation of fibers. And for that C-star action, our filtration is going to be like this. So it takes, so this guy has a what cohomology? He has like H2 and H0, right, as CP1. So what this filtration does, it takes first it takes the second class. So they have to be quantum or like kappa ideals, if you like. So it somehow goes from above to the bottom. Because if ideal takes the unit, it has to be the whole ring, right? So this is a simple example coming from this proposition. Okay, now there's a plenty of things I could compare this with, but yeah, okay, this is a quick slide. So if you forget about symplectic like a floor theory, and if you just want to think about S1 action and differential geometry, there's a classical Atiyah-Bott filtration which filters cohomology by this, the whole cohomology breaks with this fixed locus, that's what we said. And you can just think about, these fixed components, what's the value of the moment map? So you think about the maximum value of the moment map and the minimum, and you go for maximum and you collect cohomologies all the way up to the minimum. So that's what the Atiyah-Bott filtration does. Now the natural, they come also as kernels of certain maps for the ordinary cohomology. So what we observed is that somehow this floor filtration is, it compares interestingly to Atiyah-Bott in a sense that for some small dimensional examples, it kind of refines the Atiyah-Bott filtration. So Atiyah-Bott filtration would take a chunk of the fixed locus in one go. Whereas what our filtration can do, like in the A2 resolution, it can take a single fixed locus, and it can take like H2 class here and then H0 class. So in 2 steps, it kind of refines what the Atiyah-Bott would do. So Atiyah-Bott in this simple like A2 resolution case, what we'll do. So this is okay. So there's a couple of things here. First, A2 resolution is a resolution of A2 singularity, and its core, which is like this fiber over 0 here, it has 2 CP1s. So the fixed locus of a certain C-star action here is going to fix one CP1 and one point to the other CP1. Okay, so the Atiyah-Bott filtration would then take the maximum of the moment map here in the first go, and take the minimum in the second go. So we'll have like 2 steps. Whereas what our filtration does is it takes this maximum here in the first place, but then it's going to take the H2 class here, the minimum, and then it's going to take H0 class as well. So in this specific case, of course, it refines in general. It's hard to tell, but because the support filtration really cares
When you say it's hard to tell, meaning that it's not clear if they are connected or...
Yeah, it's not clear. It's not clear in general, because in general there's no formula for this flow filtration. But what it definitely can do, like I tell what, is to kind of separate certain classes in a single fixed component in a very clear way in this case, because it's low dimensional. In higher dimensions, it's what it definitely knows is the weights, the weight decompositions. So C star action, so it has a weight decomposition on the tangent space on each fixed component. And this weight decomposition really comes a lot in some computations of this flow filtration. That's what it comes with. Okay, so then coming back to the C to the N, and this is the last technical observation before I get to applications and to Higgs moduli, is that you remember for C to the N we said, okay, you can get the spectral sequence if you consider this convex Hamiltonian, which kind of speeds up the action. So using this convex Hamiltonian, what you see is you get these columns of spectral sequence which are coming from these S1 orbits. And the further you go, it's like increasing the period of the orbits. What we did here, so it's like this technical theorem, which tells us, okay, actually you can do this game for these manifolds with the C star action, which have projection, this technical assumption. And so the outcome is that you get the spectral sequence, which converges to this symplectic homology. In particular, if it's Calabi-Yau, so you have Z gradient converges to 0. And the elements of the spectral sequence is the first column was just the origin cohomology of manifold. And the higher column are going to be cohomologies. In C to the N, we had a sphere, which was just like all of your S1 action orbits. Here you're going to have that, but you also might have some points which have which rotate faster. Rotating faster, it means they're like non-trivial isotropy of a C star action. So something which isotropy Z2 means it rotates twice faster. Something isotropy Z5, it means rotates 5 times faster. So that you don't see in C to the N, because C to the N, away from 0, it's a free action. In general, it's a locally free action outside of fixed locus. So you get these. We'll see this in an example of K2 resolution. So that's just a general theorem, and then the outcome and why this spectral sequence is important is because from here you can capture the filtration. So the statement is coming from all this construction. The class is in filtered level lambda when it gets killed by the column of period lambda. So recall in the columns you have higher periods. And then, so what I'm saying is if you know the data of your spectral sequence, you know the filtration. That's kind of if and only if. And that's our kind of main tool in computing this filtration. So you draw a spectral sequence by knowing this kind of topological C star geometric information that gives you spectral sequence, and that gives you means to compute. Okay, so let's look how it looks like in A1 resolution, A2 resolution, because those are like very simple examples. What you see in A1 resolution, there's a natural C star action which just dilates the fibers in T star CP1, and the action is free outside of fixed locus, so there's just this integral here. So, okay, what we're seeing here in spectral sequence, first in the first column is just the cohomology of T star CP1, and here what's this? That's like the hypersurface, like in C to the N it was S the sphere, S2 and S1. And here this is going to be like RP3, because that's a hypersurface here. But if you just think about characteristic zero coefficients, it's the same as S3, and then you see the same hypersurface further and further. Now, because this is Calabi-Yau case, so symplectic homology is 0, like in C to the N, you know that all these have to match up. The same game as in C to the N. Okay, because they have to match up, this guy needs to go here, this guy needs to go there, and this is exactly giving you filtration. Because as I said, filtration of this class is when it gets killed. Filtration of this class is when it gets killed here. So as we've seen, that says this. So F1 is this, F2 is this. So F1 takes this class, F2 takes the whole thing. That was our first example, A1. Then in A2 resolution, which was resolution of A2 singularity, you can have different sister actions, and they will give you different filtration as well. So the fixed locus of these three different actions is going to be either three isolated points, these two CP1s, or as we see in CP1 and point in CP1. So the spectral sequences are going to look different. Like, see with the difference from A1 resolution, spectral sequence also has this hypersurface here and here, but there are some smaller cohomologies. And these smaller cohomologies, they reflect, there is isotropies. So there are, Z3 fixed point, Z3 fixed points of the sister action, or Z2 fixed points of the sister action. So they get captured in the spectral sequence. So it's like a, kind of topological information using the sister action as well, you can get. And using that, and knowing that it has to converge to zero, you can match up these, and that's how you can recover the filtration. So yeah, so that's kind of the outcome. Like, you can easily construct this spectral sequence as long as you know the sister action and how it acts, and then from there you can recover your filtration data. Because otherwise, to compute this filtration by definition, there's no way. Okay, now we're getting in the last 10 minutes. We can talk about Higgs modular spaces. And yes, a lot of people in the audience being algebraic geometry, maybe this is like very relevant. So what Anders mentioned in his talk was this modular space of bundles, which is like a Caehler version of this. In the Higgs modular, you extend this with the Higgs field to get somehow like a hyper-Caehler thing. So Higgs moduli are defined by Hitch in the 80s, and now they're very popular. What they definitely come is this structure which we need. So any Higgs modular space has a natural sister action, which delays this, initially phi, which delays this Higgs field, because this Higgs field is like free. Here it's like it's a matrix here. It's a column between these two bundles, and furthermore they come with the Hitch vibration, right? So which is defined. Well, this should be C and this should be phi. So this is like just a characteristic polynomial of this matrix, this Higgs field. So it gives you a map.
So they were probably defined by Peter and Higgs actually.
Well,
that's okay.
I always thought that was Hitch just giving some credit to very good, important people in science. I never knew that. I thought it was more like a credit because Higgs is an important person.
Oh, well, physicists do know Higgs.
Yeah, true. They were definitely, as Hitch wrote in his paper, definitely he was inspired by physics literature and what they already maybe didn't expect it. But he wrote the maths about it. Right? What's good about them is that they have the structure which I need canonically. So the sister action is canonically given by just dilating the Higgs field, and the Hitch vibration is exactly like proper. It's sister equivariant, and this is Liouville, right? So the upshot of this story was you need to send something to Liouville, and then you're good. So all in all, like this gives any Higgs modular space a structure of a symplectic system manifold. So the thing which we need, in particular, you can talk about this filtration, about this floor-theoretic filtration on the ordinary cohomology of Higgs modular space.
There's a little confusion with phi and psi.
Yes, there was. Yeah, I mentioned. So this is phi and psi. Psi was already there for this projection, and phi is the Higgs.
That's correct.
That's fine. I wrote this slide just today, so that's why the other slides were already from before. So all the typos have been revised. Good. So the algebraic geometry side, as you guys know better than I, this has a perverse filtration, right? So I guess that's by deleting or whatever. You have a proper morphism, and that gives you very, very interesting object called perverse filtration of the cohomology of your top space. So just a kind of story, as we all heard a lot of times, that this under non-abelian Hodge correspondence you get from the Higgs moduli to the character variety, and then there was famous conjecture in Arnold's paper in 2012 where they say, well, this perverse filtration is actually going to the weight filtration of the character variety, and it's been proved by 2 separate papers 2 years ago. So that's a very important story for that part of algebraic geometry. But now our question here, so it used to be called P equal to W conjecture, I guess it's called, should be called theorem. So the natural question is, okay, well, you have this fault filtration, you have this perverse filtration. How do they compare? Can you compare it at all? And the answer is, well, yeah, we can try to do that for low-dimensional Higgs moduli, let's say, and then let's see what happens, right? So whenever you're in doubt, I think it's good to try to look at some concrete examples and to see what happens. So in 2-dimensional Higgs moduli, there are like 2 classes of examples. One are coming from parabolic Higgs moduli, and the other one are from Pantev equations. And the parabolic ones are, what's going to happen is this floor filtration actually is refinement of the P equal to W. So P equal to W here, reverse filtration of these, it has 2 steps somehow. We'll see. Okay, let me say precisely what's flow filtration here. So okay, a couple of things here. So any parabolic Higgs moduli here is a resolution of this T star E modeled by automorphisms of your elliptic curve. But what's important is that this guy M gamma here, it has its core, which is this like a central fiber of the Hitchin vibration, is going to be like a tree of CP1s according to the affine linking graph. So it's either either E8, E7, E6, or D4. So just imagine you collapse these 2s. So those are going to be cores of these correspond to Z2, Z3, Z4, Z6, and correspond to 0 in just T star E. That's a simple example. Okay, so there are like 5 spaces here total. And what's going to happen for the equal to W filtration is that it takes all the other CP1s, and then it takes the central one. Here, there, and there. That's been proved, I think, by Groening like 10 years ago. What this floor filtration does, being refinement, and I mean what it does explicitly, it actually takes these spheres according to the number here. So you see, I numbered these spheres in a certain way, and what's going to happen with the floor filtration, it takes, let's say, first all the numbers 1, the numbers 2, and the numbers 3 in the end. Here, take the number 1, take the numbers 2, take the numbers 3, 4, 5, 6 in the end. So it collapses this like number by number. In that sense, definitely refines because P equal to W just takes everything and then a central, everything, and central has the biggest number, right? So that's one thing. The other thing is, which is very interesting, is that these numbers actually they didn't come from floor theory initially. These numbers are the labels of imaginary root, right? So these are all affine algebra, like these are affine linking diagrams. So these are like root systems of affine algebras, and these numbers are exactly what's called the imaginary root for these root systems. So the outcome is this floor filtration for these guys. It somehow recovers the labels of the imaginary root, especially because even with this period. So remember, this floor filtration has this period which tells you, on which slope the class died in this direct limit. So this period is connected to exactly to the number of the imaginary root. So somehow, from floor theory, you kind of recover the imaginary root of the affine linking graph, which is very interesting. Now, that's on one hand. On the other hand, you get so the other 2-dimensional Higgs moduli come from these Pantev equations, and there are Pantev 1, Pantev 2, Pantev 4, and 6. There's 4 of them. But there are other ones, but they don't have sister action. So you need the sister action. So there's 4 of them, and one of them is the same as D4 here. So that's Pantev 6. So the affine D4 is going to give you Pantev 6. So there are 3 more spaces to think about. What happens there is this floor filtration becomes trivial there. It becomes very simple, whereas P equal to W has a couple of steps. So P equal to W appears to be refinement, not appear, it is refinement to the floor there, whereas it was the other way around in the parabolic. So in the end, you wonder, okay, well, there's no uniform rule. Like somehow floor is more refined here, P equal to W is more refined there. So what's maybe the uniform rule? Well, there's something to do with multiplicity. So on one hand, so these numbers here of imaginary roots, you can see them also from algebraic geometry perspective, because so these are the nilpotent cones of the Higgs moduli space. So what's going to happen is this nilpotent cone being like a central fiber of the Higgs vibration, it gives you some multiplicities here on the components, and these numbers are exactly multiplicities. So that observation gave us this. Okay, let's think about this multiplicity filtration. So I'm saying again, so Higgs vibration is a morphism here, and this core is a central fiber of it. But these being some homomorphic maps, this gives you a scheme structure. Scheme structure gives you multiplicities for components, and then you can just think about this multiplicity being your new filtration, being your new invariant. So these components here, they all gonna be equal in dimensions, and they generate your highest cohomology degree. Like in these two-dimensional cases, you have these spheres, they generate H2, right? But in higher dimensions, they generate the top cohomology, and you can then think about just the multiplicity of them, and that gives you filtration, starting multiplicity 1, 2, and so on. So what happens is that then they actually, so this is the work with Ziller Sabo, like somehow getting all together with this Higgs moduli spaces examples. We say that this flow filtration actually recovers this multiplicity filtration. So which we've seen. So for the parabolic cases, that's exactly this statement with the imaginary root, because the point is that this imaginary root is exactly recovering the multiplicities of these components. Whereas for parabolic case, it's those are like topologically easier, so their multiplicities are all equal, and floor filtration takes them all together. So this is like a kind of upshot. For any two-dimensional Higgs moduli, this floor filtration recovers the multiplicity filtration on the H2. So because again, floor filtration, it's like it goes from up to bottom, whereas reverse goes from bottom to up. So you can never compare them completely, but you can compare them on a single like on a top cohomology degree like here. So that's what we get for like two-dimensional Higgs moduli. And then the natural question is, what happens in higher dimensions? Like, is this like a chance that these things are the same, or how also they compare to the perverse filtration? How actually this compares to the perverse filtration as well? See, both of them come from algebraic geometry. So is there any relations? So I mean, of course, thinking about this in general, it's very hard, like doing anything in general. But there's some work in progress with Alex Minutes. And what we do there is actually we compare floor filtration, peak perverse filtration, and the multiplicity on this Hilbert scheme on T star E. So T star E was the simplest parabolic two-dimensional case. You can do always just Hilbert scheme of that guy to give you in any dimension a parabolic Higgs moduli. And we had some formulas for now. I don't want to reveal them because it's going to be in archive hopefully soon. But let me just put a point. So this multiplicity came in because we just observed that they are the same. So that was interesting, invariant to think about. But multiplicities of the components are actually interesting to in the perspective of mirror symmetry and Higgs bundles in the sense of House of Kitchen. So there's an Inventionist paper by House of Kitchen from 3 years ago where they compute multiplicities of certain very stable components. I call it like there's a definition of that and all. And the point is why they care about it, because the multiplicity of certain components should recover by mirror symmetry of Higgs bundles the rank of hyperhomomorphic vector bundles on the whole space. So the mirror symmetry of Higgs bundles, there's like many ways to say what it should be. But if you think about like Kapust and Witten, like it's a hyperkähler thing, so you should compare BAA to BBV. BBV are like this hyperhomomorphic vector bundles in the whole space, or on any hyperkähler submanifold that you have a point to the whole space. So the ranks of these vector bundles should correspond to the multiplicities of components by their mirror symmetry properties. geometry. So in that sense, it's actually interesting to compute these multiplicities because they might give you some mirror data. And we did that for Hilbert schemes conjecturally. Now, that's a paper which should appear. Okay, so yeah, I just want to say like there's something to do with the support theory, and there's some non-trivial connections to algebraic geometry. What's the general statement? I cannot tell because computing floor theory is really hard in general. In these low dimensions, what is the case is the C-star geometry of these spaces is relatively, it's like low dimensions, so things are doable. It's still doable here as well because C-star geometry we know due to the Kajima's book how C-star geometry works for Hilbert schemes. So that's why we're actually able to compute this level of filtration and to compare to these. In general, it's hard to say, but there's future. So, okay, thanks for listening.
Okay, I guess the question may be one question. You have some.
So, do you understand that you expect some P equal to W phenomena in which your filtration plays a role, which is not exactly the one associated with Higgs bosons, but has different nature?
Yeah, that's a good question. I think I was thinking about, but then yeah, the answer is, as far as understood other people I talked to, there's no P equal to W outside of Higgs bundle world.
No, that's not true. In fact, you have the potential there, and there's a P equal to W conjecture for Landau-Ginzburg model, and you have a very good candidate there because this W is already there. So I mean, there's a paper that we wrote with Victor and Kaehler, and some calculations done. It's different from also, but it's much more natural to you than the one that for Higgs bosons.
Okay, well, we can talk about it later. I wasn't aware of this. Yeah. I just remember once upon a time I wanted to think about symplectic resolutions because there are like other things which have this projection, they're hyperkähler. But then somebody told me that they shouldn't have any P equal to W is more when you have this vibration, like a Lagrangian vibration, then it should be expected. So your cases they have this like a Lagrangian vibration.
Yeah.
Yeah. Okay. So then that makes sense. So we should definitely talk about that.
More comments? Okay. We'll be back 5:10. Okay. Thank you again.
Thank you. Actually, they have it's like a version of Alice space. Yeah. It is different version of Hilbert space. It's I understand this.
Okay, let's continue. I'm very happy to introduce this group, and today we talk about contact loss of X.
Okay, thank you very much, and thank you for the opportunity to speak here. It's my first time in Sofia. I'm excited about it. And I will talk about contact loss of arcs and jets. What are contact losses? So I will start with the definition in simple setup. That of a non-constant polynomial. Again, variables, complex coefficients. And the contact loss is dependent on a parameter m. That's the order of contact with a polynomial. The m contact locus of f is per definition the jets with contact order m with f. So these are the m jets. So these are the homomorphism, the C schemes, the spec of CP with the beyond plus 1 into the affine space. Those are m jets. That's the m jet space of the affine space, such that the order of contact of this m jet with f is m. So that means, so what's an m jet? For every coordinate xi, you have to associate a truncated power series in T. So what's the order of contact? You take, instead of the xi's, the associated truncated power series, and plug in into f. And you get another truncated power series. So that has to start with a non-zero coefficient times T to the m plus higher order terms. So this is non-zero. So this is the m contact locus of f inside the m jet space. We can also define this inside the arc space. So let's just say what to do inside the arc space. I will whenever I use arcs, I put an infinity there. So instead of truncating, you remove the truncation, and it's still the same definition. I will alternate between these two in the m jets and in the arc space, because actually to understand one is equivalent to understanding the other. The truncation map from the arc space of the affine space to the m jet space of the affine space is a trivial fibration, and all the fibers are affine spaces of infinite dimension. So if you understand one, you basically understand the other as well. But at some point, it's important to choose to work with arcs, and at other points, it's important to work with jets. I'll try to highlight a few of those points along the way. This one is infinite dimensional, as I said, but if you look at the version with inside the m-jet space, those are finite dimensional schemes. And the advantage of the contact loci is their equations are very explicit once f is very explicit. So let me tell you, for example, how to compute it. in the case of the cusp. So an arc or a jet is replacing the x and the y by some truncated power series, or untruncated if you're relaxed. In particular, we see that these are the coordinates of the arc space. You see why this is an affine space of infinite dimension. If you look at the k-jets of the affine space, then you stop here, and you get that the space of k-jets of the affine space is another affine space. So when we plug this into F, you get the constant terms in T, and then powers of T with their coefficients. And the FJs are coefficients in the XI with I all the way up to J, and YI with I all the way up to J. And if you want, for example, the third contact locus of F, then this is given as the zero locus of the F0, F1, F2, and then we remove the zero locus of F3. And there is a way to compute these coefficients here very easily. So I think for this I'll have to change a little bit the coefficients, make this look like Taylor series. So I have to divide by the factorials and so on. But then if you do that, x0 is x, y0 is y, and then f0 is f, the constant. And then you define a formal derivative on the xi's and the yi's by sending xi to xi plus 1 and yi to yi plus 1. And with that formal derivative, f1 is really the formal derivative of f. So in this case, f1 is 2y1 minus 3x squared x1. And f2 is the formal derivative of f1 and so on. So you get very explicit equations here for the contact loci. However, the big disadvantage is that we do not understand even basic questions about these contact loci. For example, their reducible components, connected components, even basic topological questions. So that's actually what I will talk about now. We do understand quite a lot about the cut and paste structure here, namely the classes in the Grotten group of varieties. I will say something about that too. But before I do that, let me say how one can generalize this setup. So, instead of the affine space, we can take the ambient space to be any smooth, and in this talk I'll take it to be a complex algebraic variety. So smooth variety. And instead of F, we will take a reduced divisor, or a divisor, doesn't matter, effective divisor. That would play the role of F equals of 0. And sometimes it's also helpful to focus your jets or arcs at the singularities of this divisor, because you really know very well what happens outside the singular locus. There's no mystery there. So sometimes you focus the centers of your arcs to lie in some closed subset of the support of D. So that's a more general setup for the M contact locus of arcs or jets on X. The contact order is with respect to D, and the centers of those arcs lie in sigma. Another thing that you can do is to consider a refinement, and that refinement, I'll denote it by a bar. It is restricted M contact locus. That refinement is imposing the condition that our coefficient here is exactly 1. You can do that refinement when you are in the affine setup. Otherwise, patching might not work. So imposing that this coefficient here is exactly 1 makes things a bit more difficult, but you have more structure. One of the structures that we have, for example, is that on the M restricted contact locus, you have an action of the M roots of the unity. If you plug in the M roots of the unity if you multiply T by M root of unity, you still get order M and coefficient 1 here. And that captures more things. Why I was personally interested to start with in contact loci is the following. So they are basic building blocks of motivic integration. They play a role in the theory of a motivic set of functions of the F and the Z. What is a motivic set of function? So it's a generating series for the classes of the contact loci or restricted contact loci. It doesn't matter if I'm in the infinity setup or not. We can make sense of that. Let me just take it out infinity here. So it's a generating series for their classes in an appropriate Grothendieck group of varieties. Those are complex numbers. That's the so-called naive motivic zeta function of f, for example. If you use the restricted contact loci, so with this other restriction from here, then you can impose more structure, namely that there's an action of a group of roots of unity on those varieties, and then you still do cut and paste operations. Anyway, then FLZ proved that this is a rational function in a certain sense. Being a rational function, it admits a certain notion of poles. And their conjecture, which actually was a conjecture of Viguza in the Piatti case, for a certain zeta function in the Piatti case, which this generalizes, is that those poles, so the poles of this is the motivic zeta function, are supposed to give you monodromy eigenvalues on the cohomology of the Ludmil fiber. This conjecture is widely open. There is not even a program to solve this conjecture right now. So, we know quite a lot about these classics here. For example, the fact that there's a rational function in T means that we understand something about their classes of the Grothendieck group of varieties. But we don't know enough to get any more ideas. So one of the things we were trying to do was to actually go back to the contact loci themselves and try to ask some global topological questions. Yes.
I would ask you for the notation on the top of the right side. So if we have an arc in X and infinity, how this arc, I cannot understand, it is the centered at D, or it is centered at D and at sigma?
No, you look at, so this is the subset of arcs on X, with contact order M along D.
Contact order with D is M, I see.
And their center is in sigma. So here, in that notation, this is, and I put the whole support here instead of looking at singularities.
Thank you.
Is it possible to say why you might expect this conjecture to be true?
Okay, that's another story. So there is another zeta function. It's called the Archimedean zeta function. You can complete things about it, and classically it was known, and it is known, that the poles of that zeta function are give eigenvalues of the monodromy on the cohomology of the Ludmil fibers. And the Gusa was looking at his zeta function. So his zeta function was coming from a generating series for solutions modulo P to the M, when P is a prime number, and M varies, of a polynomial, let's say, defined over Z. And he computed some examples, and he got the idea that that might be true also in this case. But there is no conceptual reason.
But do we have wave conjecture kind of thing for these zeta functions?
Who?
Wave conjecture kind of thing.
No, this is very different than the wave conjecture, than wave, because it's got to deals with F modulo P to the M.
Yeah, but I mean, if we put like that, I mean, so this is rational function you said, right?
Yeah, but still, there's no more that I can tell you. Well, there is something more that I can tell you about this conjecture. It's actually expected that the poles out giving roots of the best is not a polynomial of f. And in fact, it's expected that the orders of the roots of the B function to best is not a polynomial beat the orders of the poles here. But more than that, there's not really.
Are there some specific cases when this is known?
Yes, so in fact, in all the cases that one has looked at it and one could prove this, the first non-trivial case was the one by Gusa, pre-homogeneous vector spaces.
Say it again?
Pre-homogeneous vector spaces. Then Lezet proved it for plane curves. And since then, there are a handful of other cases that people know. Yeah, so I don't promise that whatever I say now it will lead to the monodromy conjecture, it's just we don't have any idea. So what I'll try to address in this talk is two questions about the global topology. One, how to compute cohomology of these things. Secondly, how to compute irreducible components of these things. And the first question seems to have a connection with symplectic topology, so it might also serve as a where's the atoms here type of question. Now, before I do that, before I state the results, let me state a dream situation. A dream situation, or almost a dream situation, is for the hyperplane arrangement. This is a result in twig. So if F is a hyperplane arrangement, so that means the product of linear polynomials, it doesn't have to be reduced, then the M contact locus of F, you can describe it completely in terms of complements, like very explicitly, complements of associated, there's a way to associate things, hyperplane arrangements. And because these are complements of other hyperplane arrangements that you get from here, you can apply a theorem of Orlik and Solomon, which says that the cohomology ring is a combinatorial invariant. So you know the cohomology ring of this explicitly is a combinatorial invariant. And here, let me point out the difference with the restricted contact loci. I'm going to assume here that this is a central hyperplane arrangement, so F is homogeneous as well. Then the restricted contact loci are, instead of complements, they are the Milnor fibers of those associated hyperplane arrangements. And here we bump into an old folklore conjecture that says that the Bethe numbers of the Milnor fibers of hyperplane arrangements are also combinatorial, but it's unproven for now. So this gets as close as to an ideal situation as we can expect. Okay, so before I tell you the results, I have to introduce you to the setup in which the results are nice to state. And in the setup, I'll also basically tell you almost everything we know about the cut and paste structure of the contact loci, the piecewise structure. So to do that, so X is our smooth ambient space. We take a log resolution of the divisor, D, and of sigma we blow up everything until it becomes a simple level crossing. We call this mu. And we'll write the inverse image of D as a simple level crossing divisor with multiplicities ni. The indices EI are contained in some set S. We'll also write the relative canonical divisor. I define ui as the coefficient, so ui minus 1 is the coefficient in the relative canonical divisor. And there's one more thing that we will do. we will assume that this resolution is M separated. Because we want to deal with the M contact locus. M separating means the following. Every time EI and EJ intersect, and they're different, then their multiplicities sum up to something bigger than M. Okay, in this setup, contact loss and restricted contact loss doesn't really matter. Jets or not doesn't really matter. So we can partition this into things that we know. We call this parts. So what are these? Here I would like to use arcs. This is the set of arcs in the M contact locus of D, which lift uniquely. They lift uniquely, by the way, because this is a proper map. So there is valuation criteria of properness. If you have a divisor here in the cast and some arc like that, then it lifts uniquely up on the resolution. So arcs which lift to EI but not intersect any other EJ. I call that EI naught, so the open stratum of EI. So that unique lift always exists. And it's important to have a separating condition for that. Once you have that, then these arcs, when they lift, they still have to have M contact order with the lift. So therefore you need to put the condition that Ni divides M. And then you also want to come back to the center in sigma. I'll call this set here as M. This index set here. Now, we know everything about this. So we know their dimensions. We know, for example, these are not empty. They are smooth. They are homotopy equivalent. To almost to EI naught, but in fact you need to take a canonical cyclic covering of ununified cyclic covering of EI naught. So there's the fibers over EI naught being Z over Ni is the multiplicity. So we know everything about this. One difference here is if I remove the restricted version and look at the contact loci in the MJet schemes, the contact loci and non-restricted ones, then instead of looking at this canonical cyclic covering, I'll have to replace this by the circle normal bundle to EI naught. That's one slight difference, but we know everything. So it's this knowledge here that leads one to prove results of the type the motivic zeta function is a rational function. Now, the problem with this is that this is a partition into locally closed subschemes, smooth, that you know everything about it, but it's not even a stratification. So we don't know how these things close up either. That's the problem here. So we try to look at the cohomology of this contact loci, and so this is together with Javier Fernandez de Bobadilla. Lecky Tonk. And Hong Duc Nguyen. So, to complete the cohomology here, we first fix W, a relatively ample divisor, and this mu is. So that means W is ample on the fibers here. Then with this W, there exists a cohomological spectral sequence. with you on the page completely described in terms of the resolution. Which converges to the cohomology with compact supports of the M contact locus, restricted M contact locus of F. Let me just state it for you. You can do it in more general, but let me just state it for F for now. So if you look at the spectral sequence, okay, there's some technical things there that's not going to make any of you happy, but it made us very happy because Mark Ludmil and the spectral sequence with the same one page converging to the fixed point flow cohomology of the nth iterate of a symplectic representant of the geometric monodromy on the Milnor fiber if F has an isolated singularity. So if single locus of F is isolated, and I should, for that, I should say that we work here. We can stick any sentence if we want here. So we can put any sigma here. Yeah, and sigma should be there. So, in fact, we saw first Maclean's paper. We saw that spectral sequence on that page, and we thought, hold on, but we've seen that in the theory of arcs, and we think there are connections. So we conjecture that.
How essential that this is isolated to the argument?
How essential? For us, it's not. So we don't have any assumption.
Yeah, but for him, it is.
For him, well, there is no definition that I know in the literature of the fixed point flow cohomology beyond the of the monodromy, geometric monodromy beyond that case. In fact, even yeah, I don't know. That's a question for symplectic topologists. No. I think the feeling is that it's not essential, but it's not in the literature.
So what's mean fixed point?
Fixed point
outside of Milnor fibers.
Sorry?
I'm saying that there's no definition outside of Milnor fibers.
No, I'm saying that there is no definition outside the case when you have F that has single locus of dimension bigger than 0, strictly bigger than 0. Yeah, so this is, if you have, so the Milnor fiber is really defined with respect to one point, one chosen point in the singular locus. But if there are more than one point, then you have more, infinitely many choices. So I suspect this is just a technicality.
Could be, yeah. I just know that there's a general construction for, if you forget about Milnor fiber, just like a little domain, and then you assume which Hamiltonian you want to take, and then there's a construction of this fixed point for that. But that's not the same. You're thinking about Milnor fibers.
This is really the, yeah.
Meaning maybe those intersect exactly.
Yeah, maybe I should try to do so in case this is Milnor monodromy. In fact, it's a symplectic representative of the Milnor monodromy. One has to carefully construct that. So we conjecture that this is not an accident. This is called dark flow conjecture. So if I want to compass support of F X is the same. There's a shift in the grading, but let's not worry about that. As the fixed point Frankov cohomology of the nth iterate, if at least in this setup, so isolated singularity case.
So the point is you have the same E1 pages, but you're not sure where the differentials are.
Yeah, that's what the devil lies in the differential. The conjecture is okay for M being the multiplicity. We showed it in the paper. And the conjecture has been recently proven by two students of Javier and I, Javier de la Bodega and Eduardo de Lorenzo Poza. It has been proven, so they proved this from plane curves. Of course, the proof is not really what you want, because they take one side, the algebraic side, they compute it, they look at the symplectic side, and luckily in this case it's a topological computation only, it's not really too much symplectic topology involved, and they show that these dimensions are the same. Ideally, you would want a proof that allows you to say, look, this symplectic thing is algebraic in this sense. And one of the fun things about this conjecture is that you have an algebraic, you don't have to pass to any mirror to have an algebraic computation of something symplectic. Also, the conjecture implies, the conjecture is true if you apply all the characteristics. So that is a theorem, another theorem of Deneuve and Roser. So the Euler characteristic of the M contact locus is, the Euler characteristic here has been known for a long time, is the mth Lefschetz number of the Mohr-Noether reaction. So summation I minus I raise of the mth, trace of the I here is okay, hi of the Müller fiber. Yes.
So this relation you have M on both sides, right? In your conjecture.
Yes.
Is it clear at all when you change M like from 1 to 2 to 4 whatever?
No.
How these two it's
no. So actually, this is
some induction.
There are some ideas to explore now. Namely, there is a pair of pens product here that we have never seen it on this side. So one of the next things to look at is to define algebraically a pair of pens product contact glossa. We never looked at that, but
so the pair of pens there would go from M and N to M plus N. Is that what happens there, or like
yeah, exactly.
There's not on a single one. You just need to change M.
You should be able to change M here. No, you can keep M and M prime. They could be equal.
I see. Because I never. This is like from M and M you go to 2M with pair of pens. So you're saying, So in that sense, there should be something.
Yes. I don't know. I've just seen a talk in Miami 2-3 weeks ago by Ben Ziebert looking at the ring form by taking direct sum of this and the products there. They conjectured in one of their setups that is related with the intrinsic mirror that they construct. It's tough to keep up here. This thing. That's all I have to say about this in relationship with Fleur theory. The next question that I address deals with the irreducible components of the contact glossa, and that's called the embedded Nash problem. So the embedded Nash problem, this was posed by Hein, Lazarus, in 2004. It's elementarily asks to determine geometrically the irreducible components of the M-contact loci. And technically, in terms of that M-separating log resolution that I just erased, it says which one of those exceptional divisors give irreducible components. So remember the arcs that live uniquely to EI, that's how we partition our M-contact locus, and the irreducible components must be closures of things like that. So which EIs give irreducible components? Of the M-contact locus. You can restrict it or non-restrict it, doesn't really matter. We don't have a full answer to this, we have a partial answer. So this is with Javier Fernandez de Bobadilla again, the two students. And Thomas Pelta. Suppose that one of these irreducible components upstairs, EI, of the inverse image of your divisor D, is not contracted on a minimal model of a log resolution. You don't need to assume I'm separating here. Over X. So you do the minimal model program, so you have X. You took this log resolution of D, and now you want to do a relative minimal model program over X. So you need a pair. So let me just get the pair here. Y and the divisor. The divisor is going to be the pullback of the reduced. So you do. So this is the divisor here. You apply Mori's minimal model program relative over X, and you get some other pair. Delta here. And that's a minimal model. That means the fibers, so the relative, so the low canonical divisor is an F on each fiber. Then we have an irreducible component of the M-contact locus. Of Xn for all M divisible by the order. So this is a partial answer for the embedded Nash problem. On the other hand, if you look at minimal models, which is how these are the outcomes of the minimal model program, it explains completely all the divisors from here that do not get contracted here. This is another explanation that did not exist before in minimal model program. Now, this is an analog of the classical Nash problem. The classical Nash problem does not deal with the embedded setup. It deals with a singular variety. There's no divisor here. It's a singular variety. And there, the classical Nash problem asks for the geometric determination of the irreducible components of the set of arcs which pass to the singularities. The analog of the statement for the classical Nash problem was proven by Tommaso De Ferney and Roy Docampo. In that setup, in the classical setup, that theorem already implies a full answer to the Nash problem in the surface case because of the existence of minimal resolution of singularities for surfaces. The Nash problem for the surfaces had been proven earlier completely by Javier Fernandez de Bobadilla and Maria Pepereira. In this case, if you look, for example, at plane curves, you do not recover fully a full answer to the, you do not get the full answer of the embedded Nash problem. So you need to work more for that. But we do have that. And I'll just state it like this. It's a full combinatorial answer. For the embedded Nash problem for plane curves. I should say that in this paper we only did it for the unibranch plane curve case, but then the two students in their paper where they proved the arc-field conjecture for plane curves, they extended that beyond the unibranch case. So let me tell you, in the unibranch case, to keep things simple, what is this algorithm to determine the irreducible components of the contact laws? So you take the minimal resolution of your unibranch plane curve, and its minimal resolution looks something like this. That's the strict transform of the curve, and we don't worry about that because we're looking at arcs that has to do with singularity. So, but then we have other vertices. However, as we said before, to look at the M contact locus, it's better to take an M separating log resolution. You can get that very easily combinatorially. Every time you have two exceptional curves intersecting, you add the multiplicities, and if that's not bigger than M, you keep blowing up. You can always achieve an M separating log resolution by blowing up these intersections when that's not achieved. So, at the expense of maybe blowing up some points there, you obtain the minimal M separating log resolution and its dual graph. And now remember that we're looking at those exceptional divisors with multiplicity and I dividing M only. So those exist possibly here, 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 and so on. They're sporadic, yeah, but now all of them divide. Any divisor with order, the multiplicity dividing M that appears on the horizontal bar, gives an irreducible component of the M contact locus. Moreover, those are exactly the ones given by this theorem. Now, there are other possible components that come from legs like this, from vertical legs. Let's say maybe this one is not there. Each vertical leg, as long as it has one of these divisors with an I dividing M in it, also contributes with the unique irreducible components to the M contact locus. And those are all the irreducible components of the M contact locus. Moreover, the vertex that's closest to this rupture point is the one that dominates and produces that irreducible component by taking the closure. It could be that there is that just point here, which in case we already know that there is an irreducible component. The only other ambiguity might happen here, in principle, but if there are in this vertical bar vertices with an I dividing M, we show that it can only happen on one side of the bar, but not on both. Therefore, the notion of which one of these is closest to the rupture component makes sense, and the algorithm is still the same. So that's the algorithm. Let me illustrate it to you for the cusp. So for the cusp, the minimal log resolution looks like this. You have to blow up 3 times. And I'm going to put here the multiplicities of the divisor given by F up on minimal resolution. So it's 1 here, 2 here, 3 here, and 6 here. So the dual graph is this one. Like this, the multiplicity is 1, 2, 6, 3. And now I would like to compute the 8 contact locus. So we know that we have a partition of the 8 contact locus into, well, let's see. First, we need to get to an 8 separating log resolution. So 6 plus 1 is less than 8. We blow up one more time. We look at E4, where multiplicity is 7. 7 plus 1 is equal to 8. We blow up one more time. And now we get that this bar here satisfies the 8 separating condition. But now I have to blow up this point one more time. That's E6, the multiplicity 8. Now, this is the minimal 8 separating log resolution for the cusp. Which divisors have multiplicity dividing 8, exception divisors? This one, and this one. So at this point, we know what the partition of the 8 contact locus is. Arcs which lift only to E1, arcs which lift only to E6, and arcs which lift only to E5. The algorithm that I mentioned there says that everything on the horizontal bar here produces an irreducible component. So that's irreducible. It's already explosion. And here we have an irreducible component coming from these two, with the vertex closest to the rupture vertex giving you that irreducible component. So this is another irreducible component, and that's the closure of E6. As a byproduct, so those are two irreducible components. They're also connected components, and in fact, this is a fact about the plane curve singularities. The irreducible components of their M contact loci, given by this algorithm, also are the connected components of the M contact loci. And I think that's all I wanted to say. In the interest of time, I should stop here. I'll take it further. Other questions or comments?
So, is it expected that there is a deeper connection with using mirror symmetry with the work of Martin and the floor theory in general, besides the virtual theory?
That's why I'm here at this conference, to learn more about these connections. Yes.
So then advantages they use motivic integration techniques to prove the result of the theorem?
Yes. Well, that was their first proof. Yeah, so the motivic zeta function, so this contact loci, via the motivic zeta function, they capture any singularity invariant you want, as long as singularity invariant is expressible in terms of cut and paste things. Any other characteristic type of invariance. And the Lefschetz number, the Lefschetz number is one of these things, but there are many others, like Alexander polynomials, Hodge spectrum, and so on. That was their first proof. But then Lozer and Kazhdan, Lozer and Khrushchevsky and Lozer, they came up with a second proof without using log resolutions, and that's in some sense what you want. You want proofs that don't use log resolutions anymore.
But they use logic proof.
They use the motivic integration over Grothendieck-Grubel formulas if you want. Yeah.
So one question, like maybe it's a basic thing, but because you said that you need these covering spaces to define the zeta function, right? The EIs.
Not to define the zeta function.
Not the zeta function, sorry, but to compute the cohomology, right?
They come up from these parts. These parts are homotopically equivalent. Well, in this case, these are not restricted. So, in this case, if I don't restrict them, then this is homotopically equivalent to the normal circle bundle. I don't know how to denote that. Yeah.
Right. Okay. And so, okay, so in this result, by like about the Euler characteristic there, like, well, because the point is that what I mean is that you need to have this action, like this mu action that you get when you do this covering, right? Because you consider the covering space, and then you have like a roots of unity.
Yes,
action.
acting on these guys.
Yeah,
The
exactly.
restricted ones, yeah.
But when you compute this Euler characteristic, you are not considering this, or are you? Or is it?
No.
Yeah.
No, that.
So, is there some similar result where you take this action into consideration, like some kind of equivariance thing? I don't know. Maybe it's like a very broad question.
There should be. Off the top of my head, I can't think of what is going on the other side. Yeah, actually, I don't know. That's a good question, but there should be one. Yeah.
Okay, let's think that way.
thank you very much for the invitation to talk. So, the last talk of the day, long day, so I'll use this as an excuse to give a sort of speculative talk about mirror symmetry, essentially. At least a corner of mirror symmetry, the way I like to think about it. And one comment that I would like to start with is the fact that this is a conference on theory of atoms, and if I understand correctly, one of the, I think that's an important comment, which maybe was not emphasized, especially for the people who haven't seen talks about this. I wouldn't say understand, because I don't understand much, but is that the point that the whole theory of atoms, that one of the main points is to avoid mirror symmetry. So we don't want to do mirror symmetry. We can sort of use mirror symmetry for inspiration, but we want to do, in order to obtain results about bidirectional invariance and all that, part of the, I mean, one of the most important things is not using mirror symmetry, as I said, and use mirror symmetry as an inspiration. So this talk, unfortunately, is about mirror symmetry, but the point of it is still the fact that, I mean, the background is that we want to use this sort of mirror symmetry inspiration and perhaps do things without mirror symmetry. And I'll try to explain that. So the intuition so one way to look at this is, so I'll write something which is very vague. So homological mirror symmetry for families or in families. So we sort of have a superpotential usually. And here a map, and that's kind of a little special to this talk. I'll call it check. So vibration over a parameter or that parameter space. So for those who are interested in mirror symmetry, in a way, they know that in a way the most interesting things, or the novel aspects of this, seen talks already, is to happens on the A side. So in a way, if we goal, I'll put it in quotes, is to try to do to understand the push forward and again I'll put here something like that of some kind of Fukaya, maybe wrapped, I'll put words here, wrapped Fukaya, Fukaya-sidal, and all sort of many versions category, which will be some kind of category on U. So category, well, you can think about it on category, some kind of push forward with, I should say, with maybe categorical coefficients. So this is, I'm not mentioning the word, but I'll mention it, is some kind of this idea of I'm not going to delve at all in this. So the main difficulty has to do with the fact that there is usually this map, there is a discriminant locus. In U, and so the fiber-wise picture is on the hand. The fiber-wise picture is complicated there. So again, this is something we've already counted here. So what are the approaches here for this? Is approaches. If we don't want to be
question. So this discriminant locus is related with ramification theory.
Yes.
Right? So
yeah.
That's the problem.
Yes, there is some ramification of categorical, which again I don't know even how to define, but essentially yes, exactly that's a problem. Yes. So okay, so now how do we try to do this? Well, we usually try to write periods. That's more use periods. So this is more classical point of view. Or these days, I guess it's already not these days anymore, but there sort of seem to be developments. Think about this, and again, I don't have much to say anyways here, but think about this U as some kind of space stability conditions. A la Bridgeland. And try to understand in that context what it means to approach the discriminant locus. And it seems that there are some developments here recently by Bridgeland, Ludmil. I think he thought about this, maybe he wrote something about it. Bridgeland also, and some of his students, and Halper Leisner, I think recently has some approach to this. So again, I'm not going to say much. So the point of view, as I said, I'm going to cheat in a way.
Sorry, I don't understand. But U was some arbitrary parameter space?
Sorry?
U was some arbitrary.
Yeah. Well, I mean, it's not arbitrary. We'll get to. It's a family of. It's a parameter space that parametrizes. If you want to think about the space of stability, you can think about it as an intuition as the space of stability conditions, for example. Or if you want, you can also think about it as kind of the Caehler, the stringy or a slice in the Caehler, what they call, the physicists call the stringy Caehler moduli space. So.
But the Schober picture is actually supposed to make sense for any symplectic vibration.
Yes, but yes, but in this context, I don't want to talk about the general picture. You're right, absolutely. So the B side. So the B side means we're going to talk about try to understand something like the bounded derived category of coherent sheaves on XA, where A is a parameter, and use asymptotics to say something about, to study the behavior at the discriminant. So I'll make this more precise, at least in cases that I can say something about. So, okay, so now I need to introduce, sometimes in this type of conferences, I don't do that, but I still, I feel like I want to say something here about spherical functors.
So you use W, you mean matrix factorizations?
One version of it could be matrix factorizations.
Because here you have BB core, it doesn't CW or
Right, so I mean, when I say here, when I write this, I also assume that the case where there is no superpotential, by the way.
Okay.
So
this is the W equal to C.
Right, and I could, a version of this would be the matrix factorizations, right? So that I want to explain, since this is more geometrical, what a easy spherical functor is. So it's a spherical functor. For those of you who saw, I'm gonna write the definition here. So let's say this is Q, so it's a flat. So let's say X, E, Z are smooth, quasi-projective varieties. And I need to assume that Q is flat and proper over Z. Then then definition, we say that the following map from dB of to dB defined as I star. So we first pull back and then push forward. Defines an equivalence of the category dB Koch of X, and with given, so the equivalence is given by the twist, and I'm just going to write the formula as the cone of I star Q upper star Q lower star. Sorry for this. So that this is a map of functors. So the cone would not make sense. It turns out that if we enhance this picture and work with DG categories, we can enhance this to a well-defined definition. And the categorical action is given by this cone of, so there is a morphism here, and these are basically just the natural adjunctions. So it's kind of, from that point of view, is very, it's a very natural definition. And for those of you who are more familiar with this, this is easy spherical. So this, we can think about this, first of all, this is sort of a family version of this, of the Seidel-Thomas spherical object definition. That's one observation. The other one is dBz, dB. I should maybe give up on this. Oh, yeah, I'll give up soon. turns out that this is spherical in this language, in the formal language, in the language of Ano and Lormienko. And of course, this is sort of a now the question is, why am I talking about spherical functors? Well, the reason is that spherical functors, or easy spherical functors, are really ubiquitous. Can I spell this? I think so. In categorical birational geometry. So they're as present as the semi-orthogonal decomposition story, which appeared already in many situations already. So let me first mention this result of Halper, Leister, and Shipman, which says that, and again, I'll just present the formal version. It says that A to B spherical functor induces a natural, I'll put this in quotes, semi-orthogonal decomposition of a category C whose so in a way, if we think about this story, talking about semi-orthogonal decompositions is the same as talking about spherical functors. So then the other result that I want to mention, famous and most of the people here know it. So if we take a blow up, so let's say everything is good here, smooth, projective, we're avoiding all sorts of complications. So this is a blow up with a smooth center. Let's say this is x plus, x minus. Then Orlov says that there exists semi-orthogonal decomposition where you have dB of, again, as I promised, I'm going to give up on the writing Koch from VIHREN, x plus as the pullback of dB of x minus, and a bunch of copies here, in this case, I guess d minus k, copies of dB of z. So, by the way, since we're here, let me mention that essentially, and this again has been mentioned, I believe, at least maybe in a couple of thoughts, essentially that this is, we want to, as I said, avoid mirror symmetry. This is exactly the context where if we want to do the theory of atoms, what one needs is the analog of this result for the associated quantum D modules.
I think it's d minus k minus 1.
D minus k minus 1?
Imagine you blow up a divisor, so this is isomorphism, so you have no addition.
Right. Yeah. Projected space, right. Okay, so so now let me write down, since Ludmil came, let me write down this speculative And by the way, I should say something, but hopefully I'll have time to. I mean, I don't have much to say, except that in this definition, which I erase, I just erase, of a spherical functor, and that maybe connects to Victor's. That's why I remember with Victor's talk. In the definition of a spherical functor, in fact, the generic fiber is a Fano. So we can think about geometrically also about this as a flat family of Fano degenerating to a flat degeneration to a possibly singular. So maybe I'll say a few words about that. Maybe. So so let's say general conjecture. I don't even actually. I'll say expect of it. The last talk of the day, so please forgive me for. So this, I'm gonna try to explain the sort of a general picture, but combined with some results that were proven by other people, were also some results that we proved together with Ludmil. So first of all, about this, there is something right, so, and I'll try to explain this more carefully in after I write the general conjecture. So and at least in the toric case, this conjecture was made by a Aspinwall, Plesser, and Wang. So it's a string theory conjecture. And essentially, again, I'll write a very cartoonish version of it, but it says the following thing, that for each component of the discriminant locus, and let me call this component gamma, there exists an easy spherical functor. Yeah, so now I guess I have to go back to what Pranav mentioned. So I'm going to assume that X is Calabi. And in particular, there is this easy spherical functor of the following form dB. And I'll call this so these are where Z gamma is combinatorially defined. So, in fact,
so in this conjecture, what is U? Is U some subset?
Yes. So the gamma is a component of the discriminant in U.
And U is some subset of some compactified space of stability conditions? Or?
Yes, you can think about it like that. Or in this toric case, we really have, for those who are familiar with this notion, in the toric case, we do have at least an approximation for this as the toric stack defined by the secondary fan associated or secondary polytope associated with the toric picture. But maybe I'll.
So is it known that the secondary thing is related to stability conditions? Or is that conjecture?
I think I mean, the expectation is absolutely that. Now, if there are cases certainly where you can prove that if you take the right motion of in the cases when we know the space of stability condition, if you take the right motion, you do get this stack. But there are not that many, since there are not that many where cases where we actually do know the space of stability condition. So the other aspect I should mention here that about the connection with the space of stability conditions is that the reason I'm doing this way is also because I'm trying to understand the global picture, and that's very, very hard to do if we work with stability conditions. So we can sort of do local stuff. So now a refinement of that is that there exists a Whitney stratification of the discriminant locus such that if we have two strata, let's say gamma 1, then we have a diagram in fact, if we work in this Calabi-Yau case, this is just going to be an equivalence of categories. So here, sorry, let me write it again. This is a semi-orthogonal decomposition. And these are spherical. In a way, the way I like to think about this, also inspired by and there is some connection with the actual D module story. So at least in the toric case, this is really has the picture. If you translate the picture in terms of D module, this is a version of a Riemann-Hilbert correspondence. So now.
What's the connection to D module?
Okay. I'll try to say at least one word about that. So I cannot, because then that would require me to present this in the toric case. Present the whole machinery, but I'll say at least a few words about it. Maybe I'll say it now. Let me see how I can. So let me maybe finish this third part of this general conjecture. So again, in the toric case, important for us is that, so here, as I mentioned already, in the toric case, we do have so U can be thought of as the Lie force taxa. And I'll say a few words more about this. Induced by the secondary fan force stack. And I'll explain this, but I just want to state first the property. So if you accept this, then the statement is that, and this is somehow surprising to me that's not in literature. I think we can actually prove it. So for each open stratum, open toric stratum, say S in, so essentially, if we ignore the stackiness, S is some kind of open torus. There exists another easy spherical functor, which looks like this. It's dV. Here I will write Zs to dVx. So this x is the ambient labial, where Zs is combinatorially defined from S. So let me try to say one word about the geometry behind this. So essentially, if we work in this toric case and we concentrate our attention to just an open stratum, this is, of course, we know this is complicated, that we have to do if we want to analyze even classically the monodromy. However, there is one important thing. So inside, so this comes from the combinatorics. There is only one component of the discriminant which is irreducible. So the difficulty of the global picture here with this discriminant is that the discriminant that we're talking about has lots of components, and the intersections are complicated. So there's no hope of studying them directly. However, in the toric case, we have this nice sort of sub-problem, if you want, that if you take a toric stratum and inside the toric stratum, there is always a hypersurface, which may have bad similarities. But that's the one component of the discriminant locus. So categorically, this what this easy spherical corresponds to is exactly the monodromy around this component. So the difficulty, of course, all this issues about how the strata and the Whitney stratification appear has to do with the fact that what happens when you put the toric strata together and how these irreducible components match. And then, of course, we get into classical problem that we know that they're, well, complicated. And I should say that this, for one-dimensional strata, if dimension of S is 1, this has been studied. It has been studied, especially by physicists, believe it or not. Mainly by Aspinwall, but not only. And it goes to, he calls it the wall monodromy. So he calls the mirror to what you would have if you do mirror symmetry to a loop. He calls it the action, the categorical action, the wall monodromy. Okay, so what I want to do now I'll try to finish, not to go over time, I'll try to actually explain a little bit of the part that we can actually do and say a few words about this asymptotics. How does that come about? So rhetorically, so I apologize, probably quite a few people here saw me talk about giving exactly this combinatorial talk. Here it will be much briefer. So we start with this bunch of vectors in the lattice n, and we assume that they sit in a hyperplane. So H of VI is 1, H linear. And basically, say we call sigma a fan supported on A. So what that means that all the rays in the fan are among the elements in this set A. So this secondary fan that I mentioned, or the secondary polytope, again, there are many ways to think about it, but the polytope is, we can think about, I should rather say, this is dual. We can think about a fan of phi of thetas, where these are theta are piecewise linear, and strictly convex on this fan. So for those of you who are not familiar with this notion, for those of you who are familiar, this is a bad introduction, sorry for that. But if you're not familiar with this, the way you should think about this, basically, the way I think about it is sort of, we try to parametrize, given such a set, we try to parametrize combinatorially all the possible triangulations of this set. And one way to think about this is that we consider all the piecewise linear functions which are linear on the maximal cones. And it turns out, and this is this Gelfand-Kapranov's-Zelevinsky, I should say here, Gelfand-Kapranov's-Zelevinsky magic, it turns out that you can organize these in a fan, the so-called secondary fan, and the big cones of this fan, so if you stay inside a big cone of this fan, you'll get the triangulation. If you move to a point which lies on a smaller cone in this fan, you'll get the polyhedral subdivision. This is a beautiful story. Again, it would be impossible for me to explain this now, but it turns out, and again, this goes back to Pranav asked all the good questions. I even talked to him before. I did not talk to him before. So it turns out that the GKZ, of course, at least you're familiar with there is a GKZ D module associated to to this data. And its importance for mirror symmetry is that this is mirrored to the quantum D module associated to X sigma X, where X sigma is the toric variety determined, induced by sigma. And as I promised, this picture should be viewed as a way of trying to understand that D module well. What we really want to understand is this quantum D module, in fact. And this here, there's essentially there's a change of variable, the mirror map, and but at least in the toric case, this is sort of a story that's understood. And now going to what the comment by Pranav, it turns out that what GKZ have shown is that how should I call it? Let's call it D here. The characteristic cycle of this GKZ D module is a sum over, these are faces of the convex hull of the college of the convex hull of A, and here some multiplicities and some cycles, D gamma. But the point, so now we can go back to what I was trying to say earlier. All, in a way, the action that I was trying to describe in this with this speculative conjecture, in a way, is inspired by this formula. Because we have the characteristic cycle with multiplicities, and we sort of, at least in theory, can have try to translate, as I said, using mirror symmetry, try to translate at the categorical level anything we can say about the characteristic cycle. So now let me write what we can prove in this case with Ludmil. So you remember the statement that was part of the general statement was that for each such gamma, there is a easy spherical so the proposition is that these multiplicities are exactly the rank of K0 of this Z gamma. And again, this is just a combinatorial calculation, assuming that, as I said, we give a combinatorial definition to this variety. So what is behind this combinatorics is also this important notion, again, going back to the GKZ case of the A resultant, or we'll call it A discriminant. I'll write the definition and then I'll explain. Faces before, and this is a classical discriminant associated to this set. So if you give me a bunch of weights, if you want, a bunch of EIs, you can write down the set of polynomials and look at the classical discriminant. And the magic of this EA is that the Newton polytope of EA is exactly the secondary polytope of that's defined. So we have complete control. So if we, without this multiplications, this formula would, you know, the class, try to understand the classical discriminant is not something you want to do, except that you have like a high school problem or something like that, which is, you really want to destroy your students. But somehow magically, of course, inspired by this property, magically, if you construct this much more sophisticated polynomial, it turns out that you can actually understand the Newton polynomial, Newton polytope of that. So what we can, the asymptotics, finally I got to the asymptotics. The game we're going to play we're going to look at this formula, I'll rewrite it, maybe I'll erase it. And consider, so I'll remind you something I wrote, but I know, so so I call M the limit for stack induced by the secondary fan associated to A. So the game we're going to play, we're going to take asymptotic limits. So essentially, let me draw first a little picture. So, this is the secondary fan. So the game we will play is take asymptotic limits so take asymptotic limits in this formula star in the direction of various thetas, where theta, I'll remind you, so basically this is some theta, this is theta, this vector corresponds to theta, this corresponds to some other theta. So of course the interesting thing are going to happen if we consider a theta which sits inside these walls in the secondary fan, or if you want, which are orthogonal to various strata in the secondary fan. So the formula which we can really honestly prove here and sure there was a is that if theta corresponds, I'll write it like that, correspond without the comma, to a rational curve, to a P1 inside M in the moduli space. So again, M, think about it as a stack. We have all this strata. There is a web of P1s, and most of the studies, for those of you who are familiar with this, of this story about understanding the global structure, have been done by moving in this web of P1s. So this is M. We have some boundary points, and these are all P1. So what we can show is that the rank of K0 of ZF is actually the sum So I'll remind you what these were. So ZF was the source of V of ZF and dV of Z gamma were the sources of these two classes of easy spherical functors. And what this suggests is that, well, it suggests it's, you know, this is exactly similar to what I guess Maxime was saying. I don't know how we call it, philosophical versus legal or something like that, or I forget the term. This is the legal thing, and the philosophical thing was this conjecture. So the legal thing suggests that indeed the philosophical thing is that we do have a semi-orthogonal decomposition. Write it like this. So we have copies of Z gamma. So here is N gamma F, which are some multiplicity which are combinatorially defined. And they should have a meaning as if you try to do topology, some kind of intersection numbers in topology, but so maybe 2 more minutes, 3 more minutes. Yeah. Sorry for. Actually, we do have a formula which is much more. I'll write it because it's weird. So if we take an asymptotic limit, which is not, which corresponds to a higher dimensional stratum in this moduli space, the formula is something around like this. So it's the rank of K0 again, dV of ZF. But now we have a Newton polytope of the discriminant associated with this F. And we get the sum here of K0, again, the sources of these discriminant with so does this come from this conjectural even semi-orthogonal decomposition? I don't know. I mean, I play with some examples, and if you unwind this formula, indeed, you see that essentially it reduces to one semi-orthogonal decomposition, but otherwise it's very weird. And again, I don't have a, that's why it's not included anywhere, so written. So I should say one more thing. Talking about, I mentioned, I want to just make some remarks. I wanted to say something more, sorry, but I don't want to keep you. So just to make a connection with what Victor was saying. So the picture I have here, flat with generic fiber, F fund. So the picture that Victor had, part of it, of this, his definition, I think it was number 3, was something like this, that you take F flat, you deform to X prime, and the way I like to think about this is toric, as he said. You can correct me if I'm wrong. And then on top of it, I take a Krepin resolution. And it turns out that this X is exactly the X I'm using. So in a way, it looks like this picture is somehow a global version of where at various discriminant components, you have a phenomenon exactly similar to this story about Landau-Giltor model. So, of course, I'm cheating because he had Landau-Giltor models, and I talked about the case where the superpotential is 0, but that's really not very important, so that can be adjusted. And so this is kind of a little mysterious for me, although this is sort of understood that in a way one can say that understanding Landau-Giltor for Fano, you can think about it as sort of a subfield of understanding the toric picture. So so this sort of what's going to happen, my claim is that this phenomenon corresponds to some kind of locus inside the discriminant, inside this discriminant locus of the GKZ story. So that's number 1 comment. Number 2, something that I didn't say is that of course this is related to some asymptotics of oscillatory integrals. And periods. And then the question arises, what are these numbers? Are they some kind of spectra? And of course, inside the discriminant locus, certainly here we have some, in baby cases, you can see some kind of Stokes phenomena. But we haven't worked that out. And the other comment, of course, the elephant in the room, as I said, can we do this by sticking to quantum D modules? So do really the theory of atoms? I don't know. So I'll stop here. Thank you. Sorry.
Any other question?
So may I ask a question
about
this relation with atoms? Actually, that's one of approach to compute Grom-Fit invariance, like for Grassmannians or whatever. When you degenerate to make this manifold transition, degenerate, you have a Grom-Fit theory on your X, and Grom-Fit theory for F is a specification. So instead of some parameters, you put just ones in X.
Right.
So
you take a sort of a special slice in this discriminant locus, right?
Yeah, but so the composition of Grom-Fit invariance is what atoms are doing.
Right. So in a way, what I'm saying is that if we can translate this at the atomic level, we should have a theory like this where we know this very tiny theorem sort of. So actually, we don't know exactly in a case like this, but we expect that this sort of breaks down at the level of quantum D modules on the level. So this computation for the Grassmanni has been done.
By
Oh, I see that old paper. Yeah, I know that one. But I was curious if more recently people looked at it.
So that's maybe, but that's what I know. Maybe some developments.
Any other comments or questions? Okay, let's think more, okay?
Thank you.
Okay, guys, we resume tomorrow at 10.